So we all good for 4 o'clock, Peter, in the back room? Huh? 3 o'clock? Immediately after that? Maybe?
Yeah, we can do that.
This starts at 3 o'clock.
That's fine with me.
We'll wait just 1 or 2 more minutes. There's another session ending that people are coming from, I think.
For me, it's fine. It's really fine to go immediately after
Yeah.
this. Okay.
Let's see. But maybe the first speaker could come up and be ready. Jeff. Yeah. One more minute.
There it is. Okay. Thank you.
Let's see.
And what do I aim this thing at?
I
Do I aim it at that?
have no idea. I think it's just wireless.
What do I aim at?
Yeah, nowhere.
Okay.
Yeah.
No, I don't have to point it in any direction. Omnidirectional.
3?
Like a high quality hydrophone. Good.
Let's see.
We do it for the meeting. Is that okay?
Yeah? Yeah? It's fine.
Let's see, we're starting 2 minutes late. I'll go 14 minutes total, and I'll give you some warnings beforehand as to where you are. Okay. Okay, let's begin. Our first speaker today is Jeff Cram from the Applied Physics Lab, University of Washington, where I was for 20 years. Talking about the OOI cabled array winch profiler data for improved hydroacoustic analyses. Jeff.
Good afternoon, everybody. My name is Jeff Cram. I'm a principal mechanical engineer at the Applied Physics Lab at the University of Washington. I'm presenting on behalf of my colleagues Mike Harrington, principal electrical engineer and department head, Kellen Rosberg, who's an oceanographer, Kevin Williams, who was, until recently, was the department head for acoustics at APL, and he's a senior principal physicist. And, of course, Lisa Zirk, our executive director. So my talk will be a bit more wide-ranging than those ones you've heard so far today. I will start with a very brief introduction to the Applied Physics Lab at the University of Washington, for those of you who perhaps are not familiar with us. Go into quite a bit more detail about our regional cabled array, followed by some data from that array. And finally, I will attempt to tie it all together in terms of its relevance of the aforementioned to the CTBTO future hydroacoustic stations. So very quickly, the Applied Physics Lab at the University of Washington, formed in 1943. We're a very integrated department. We design, build, deploy, and do science on our equipment. And I should stop now and say this is not to pat ourselves on the back too hard. We we partner and collaborate extensively with other departments at the university and other institutions. And we're not too proud to contract out some specific work as needed. And one example that's coming up where L3 Maripro was absolutely invaluable for our cabled array. So our core competencies, underwater instrumentation and equipment, probably well over 50% of our work has to do with oceanographic systems. Ocean acoustic propagation, Bruce was definitely a major contributor to that while he was at the lab, and we're still carrying his torch for him. Experimental oceanography, mission-related and public service, rapid response, R&D, and engineering, that is a catch-all for all the other things that don't apply with everything else I've said, and quite a bit of simulation and signal processing. So on to the regional cabled array. This is I like to describe it to people who ask me, what is an ocean observatory? And I say it's the scientific equivalent of a pickup truck. It's power and data accessible to whatever oceanographic instruments you can conceive of. Well, I'm sure there's something that requires too much power, too much data bandwidth, but we have an awful lot of it. We developed it in conjunction with the UW School of Oceanography. We started the development in earnest in early 2010 and installed the system in 2014. Has a 25-year design life. It's going strong. And it is a undersea cabled network, star topology, and has lots of expansion. I did a calculation the other year, and I estimated that we're at about 5% capacity for power and bandwidth. So this is what it looks like in a graphical sense. We have two telecom-grade cables coming out from the mid-Oregon coast from a shore station. One of them going approximately 500 kilometers offshore to the caldera of an active undersea volcano at the spreading center between the Pacific Plate and the Juan de Fuca Plate. Another one coming also across the continental shelf down into the abyssal plain and ending at, coming back up and ending at around 80 meters depth. Every one of those truncated red pyramids represents a primary node. The cables and the primary nodes were designed, built, tested, and installed by L3 MAROPRO, for which we have a great deal of respect. They did an excellent job. Everything else, however, we built ourselves, and that includes a number of secondary nodes, or junction boxes as we call them. I'll go into some detail about them. And two innovative profilers. One is, we call it the deep profiler. It's essentially a highly modified McLean-moored profiler. It's a wire crawler, and it goes from the seafloor to approximately 80 meters below the surface. We also have a winch profiler that profiles the top 200 meters of the water column. And we have one of each of these things at 3 different locations in our network. So in summary, 7 primary nodes. We still have 5 available ports on them. 18 seafloor junction boxes, 10 ports available in them. Ports meaning wet mate connector receptacles, things we can plug things into. And since we can daisy chain, there's actually theoretically a much larger available number that we can deal with. And those 6 profiling moorings. And as of the end of the current maintenance cruise that is actually underway as I speak, we should have 150 instruments on the seafloor and in the water column. So the junction boxes, we have 18 of them. Basically, these are receptacles for power and connectivity for instruments. They come in 2 major forms, but each of them has up to 8 ports, connections in other words. And the larger one is capable of 1,600 watts of power and 4 different communications protocols, and the smaller one is 150 watts of power, still quite respectable for your average oceanographic instrument. Here's an example of one of our junction boxes being lowered in the water column by an ROV. And I'm going to give a plug for the Canadian Submersible Scientific Foundation, whose ROV this is. They were absolutely invaluable, just as helpful to us as L3 MAROPRO. In terms of their abilities for doing nearly the impossible in terms of getting things going under very trying circumstances sometimes. Here's a junction box on the sea floor. You can see an ADCP installed off to the right, and the titanium pressure housing that contains the power and communications electronics that allow us to connect to the instruments, and conversely to talk back to shore for the near real-time data acquisition. This is a close-up of one of the connector panels. Each one of these orange objects here is a wet mate connector, and they've got the big paddle on them so that an ROV gripper or end effector can manipulate them to plug them and unplug them, making sure, of course, that we've turned everything off before we do such things. And it gives this system the modularity that it needs. Here's a shot of the afterdeck of the Thomas G. Thompson, our principal research vessel, and all the different cables that were laid by the ROV. Not everything has to happen by cable ship. ROVs can lay cables up to, in our case, 4.7 kilometers in length. 150 instruments, 35 types, and I know it's more than 8 at this point, I just don't know if custom types, 27 commercial oceanographic instruments. And you can see the examples we have there. The HD camera has such a high data bandwidth that we don't plug it into one of our secondary nodes, we plug it straight into a primary node. Here is a very brief cartoon of one of our 2-leg moorings for the shallow profiler. These are quite complicated moorings, but basically they have 2 anchors and 2 principal tethers. The blue one is a synthetic line, and the green one represents an EOM cable. EOM is electrical, optical, mechanical, and the idea is that it has to hold things in place, but it also has to have optical fibers for high-speed communications with a platform at 200 meters, and it has to have copper conductors for power. The whole purpose of this rather elaborate mooring is to support our winch profiler. This profiler gets changed out every year on the annual cruise, and in between, for approximately 364 days a year, it moves up and down on the water column. The float moves up and down on the water column, studded with up to 15 instruments, 9 times a day, which means I calculated at one point it's the better part of 1 million revolutions in each direction on the winch drum itself. And it sends the data back to shore in real time. And now I will show you a 1-minute film, and I'm sure you'll all be pleased to know that I finally at the last minute refrained from attaching the soundtrack from 2001. Could you put the movie on? So here we are with the ROV suspended with suspending the shallow profiler, docking with the 200-meter platform, and then lowering the bail. The bail is the thing that carries the shallow profiler with. Then unfurling the cable that connects the shallow profiler back to the platform and then to shore. This is an ROV wet-made connector being connected. Then standing back to make sure everything looks right, after which we do a test run to have the thing go up and down in the water column just for a few meters to make sure everything is all right. And this is what it does, except not for a few meters, but for the majority of 200 meters in each direction, day after day. So this is something that is not very common out there. We're quite proud of it. It took an enormous amount of engineering effort, and it's really quite reliable, so we're pretty pleased with ourselves. Here are examples of some of the data we acquire from one of our shallow profilers, temperature and salinity with depth. You can see the changes to the thermocline and the halocline over the seasons. Each color represents a 3-month chunk, summer, winter, spring, and fall. And for another look, we have here a 2-year span of data, temperature versus depth. You can see the fairly well-developed mixed layer during the winter months when there's lots of activity on the sea surface, lots of wind, not a whole lot of sun. Then when summer finally comes, and we're all very glad when it does when we live in the Northwest, then all of a sudden there's a lot of insulation that heats up the upper layers. And it lasts, and it grows, and it grows, and it grows, until there's a fairly abrupt change and a fairly rapid restoration of that winter mixed layer happening. Here's another look at it for a 1-year span. And you can see the effect of wind, for example, which is that red trace is the 12-hour average. So it's fairly low during the summer months. And then right around mid-October, all of a sudden, the weather comes in. We call it the long rains. So we get a lot of, we get more winds, we get more storms, we get a lot of cloud cover, in addition to the fact that the seasons are changing. It just cuts off an enormous amount of insulation. And that mixed layer starts to develop so that by the time you get to December, it's pretty much there. We can look at the data also in terms of spectra. And here we see, in the short term, we see the influence of wind, for up to 6 days out. And then in the longer term, we can see seasonal effects that actually penetrate deeper into the, they create that mixed layer that I referred to. And at some point, we see annual and longer timescale effects, but you would need many, many years of that stuff to convince yourself that you actually have an effect. So why is this relevant to the CTBTO? Well, we are working with the PTS to develop a modular design for a future system in order to allow this to be a more sustainable system. The point being, if something breaks or fails, or just we want to renew something, then a modular system allows you to do it. And as part of such a system, we would recommend the idea of actually putting an additional wet mate connector port on there, so why not add another instrument? It would not in any way hurt the ability of the system to be as good as it is now. So I'm going to end with a quote by Carl Wunsch in support of long-duration measurements. Any useful ocean observation system must be open-ended in time. There is no low-frequency cutoff to the timescales over which the system is capable of change, and new physics always enters as the timescale increases. Thank you very much.
Questions?
I must have done a very good job.
I've one, this morning it was mentioned that O-rings are a limiting factor for really long-term deployments. Do you know of, or are you considering things like metal O-rings or other ways to extend life in that sense?
We don't consider metal O-rings primarily because for the 25-year design life of our system, butyl O-rings, which is what we've standardized on specifically for that reason, have a low enough moisture permeability that we don't have to. And that allows us to take things apart relatively easy, and butyl O-rings are relatively available. So they are perfectly satisfactory for our purposes.
Question? Okay, I have one more then. In one of your plots you showed over 2 years that the profiler data got closer to the surface. Was that a learning process? I think, yeah, there you go.
Well, for me as a mechanical engineer, absolutely. I'm not sure that my colleagues would have been so surprised by this.
Okay. Good. Okay, thanks, Jeff. Next speaker is David Dell'Osta, reducing ambiguity in hydroacoustic triangulation through consideration of three-dimensional propagation features.
Hello, yes, I'm David Dell'Osta, and I actually got my PhD at the University of Washington and joined the Applied Physics Lab. And I worked in the acoustics department, a different department than Jeff here. And my research has been on both analyzing data and modeling and collecting propagation data on multiple scales. And my involvement with CTBTO has really kind of expanded that to the global scale. So today I want to talk about how we can actually use some measurements on what I thought at first was kind of a sparse, there's only 6 listening stations out there, to actually improve our ability to localize events that occur. And so to kind of overview, what can we do with a hydroacoustic station? Now, I'm referring to the hydroacoustic station as one of the 6. So there are two triplets that are on the north or south end, typically at one of these stations. And when you have a triplet, you can get a bearing of arrival or a back azimuth. So you can get a direction to know where that sound source came from. We can also look at the signal dispersion and with a model, you can actually do some ranging by matching the signal characteristics as they change, as they propagate over longer distances. And then finally, kind of the part that I'd like to emphasize here is this, looking at 3D arrivals, we can actually add virtual stations because we have arrivals coming in at different times. And so on the right here, I show an example that I'm going to highlight throughout the talk. We saw this a bit earlier this morning when the ARA San Juan was lost, produced a very intense sound, and I mean very intense as nothing on the order of what a nuclear explosion would be, but one that was heard 8,000 kilometers away. And the 2 red paths there are paths that go to the red triangle, which is the listening station at Ascension Island. And the direct path is solid, and there's a refracted path, one that was first going towards the continental shelf and then was refracted by multiple interactions with the bottom. And it's actually relatively easy to model this if we take some reductionist view of how the propagation is actually going. And then there's the southern route to the Crozet Island station in yellow there. And so with these three paths, we essentially have three virtual stations, or three hydroacoustic stations. So with two stations, you can get a event time if you know a location, or if you don't know the location but you know the event time, you can get that. But with three stations, you can get a precise event time and a location. So it's very desirable to have three detections. So this, the San Juan was lost a year and a half ago, and it was discovered about 6 months ago. And I was able to access this data through VDEC, and was approached by the search company Ocean Infinity to help kind of verify what they had learned from CTBTO. And I want to say that the immediate response by CTBTO was very impressive, that they were able to get back to them within first days and then weeks to give them a very accurate location. So in their search effort, they used both what they knew the dynamics of the submarine were, and they built radiuses of probability of what speeds the submarine could be going. And they took on this kind of no-cost contract if they didn't find it. But they did find it, so they were able to get paid a fairly modest amount for how expensive I'm sure it was. And it was based off of searching the area of the acoustic detections. And just to show, let's see here, this kind of this long ellipse here is if we consider two hydroacoustic stations and we don't know the time, we don't know the position, we actually can define a line with some certainty bounds that location, that the source will exist upon. And then what CTBTO was able to do is take in the seismic recording and actually reduce that uncertainty by pinpointing that time, because the seismic travel time was much faster, and actually it was a very, very close station. So they essentially had three acoustic stations to form these air ellipses. And then the submarine was found in this very complicated bathymetry. After they had trawled that area, they'd gone over it with like a rough scan, and then finally they went back with higher equipment, in part because we had high confidence that the CTBTO data would know precisely where that submarine was. So the three recordings here, there were two triplets, one above and below Ascension Island, and then only one operational on that day at Crozet Island that was back online a few days later. You can see these are time aligned here, so over roughly 25 minutes, you could see the shorter path to the HA-10 station, Ascension Island, saw the signal first, and then the longer path in this box down here came in later, about 20 minutes later. And there actually was some discussion earlier this morning about an earlier through the ice arrival that actually kind of comes in around the same time. But I'm going to focus on the two paths at the Ascension Island numbered there, and then that path, the direct path through the water at the Crozet station. So looking at the spectrogram here, this is a time frequency plot. This is a closer look, so basically taking that signal we just looked at and looked at what the frequency content was as it is evolving in time. If we look at the Ascension Island, we have a very different looking signal than the one at Crozet. And the one at Crozet has this very distinct feature. I would say that doesn't look like an impulse to me. It has a very distinct slope, but I'll show you what that comes from in terms of a dispersion characteristic of going through an Arctic profile. And I'm focusing here just below 15 hertz. In part, that insulates me from having to deal with small-scale temperature anomalies that could actually scatter different energy into different regimes. So what I mean by scattering is scattering energy in acoustic modes. And the acoustic modes here are similar to rays, but they're a little bit more complete. But the basic idea is that you could take the wave equation and you can separate it into a vertical component, the part with depth, and then a horizontal component. And so that we've kind of taken now a reductionist view of the field here, and we can treat the two parts separately. And from the vertical part, we can actually get what the speed would be, and that's really at what angles are is the sound propagating at, where it's reinforcing itself that it's able to propagate great distances. And in the mid-latitude, we have this warm water, and then the deeper water, the pressure increases. We actually have a notch in what the sound speed is. So sound gets trapped in the middle, this SOFAR channel, or the sound ranging and fixing channel, which was actually developed to find down pilots in the World War II, where they would drop a little charge, it would make a noise, and they needed 3 stations, and with 3 stations, they could record the sound and find where that pilot had fallen into the water. So it's kind of the same idea here. If we get three arrivals, we should be able to find that source precisely. And then when you look at the southern channel here, so at the bottom plot, we actually don't have this trapping by the warm water, but we have still trapping by the sea surface. And this actually makes the mode function sample different parts of depth. And so the lower frequencies actually get to go a little bit faster than the higher frequencies. So now just taking a look, if I take a cut based on a geodesic through an ocean model, the World Ocean Atlas here, and look at the sound speed profile, I show kind of in roughly 500-meter increments here what the sound speed profile looks like. And then the bathymetry here is in the thick black line. And then you can see the group velocity is the dotted line going through the middle, and a phase velocity. Those two are very much related to each other, just a little bit above that in the solid line. And you can see as the sound would propagate over some shallow feature here, this actually being the Rio Grande rise here, there's a little fluctuation in what the group velocity would be. And similar, as you get to the really shallow region going up towards the continental slope, you have a drop in the group velocity. And so as long as you can track these, you can actually get the timing of the signal quite accurately. So let's see, I want to kind of show what I mean by if we were to take a propagation, we don't know how far it was or when it happened, and we just take one single recording here and look at what the dispersion would be. See if I animate this. Could you play the video?
There it's going.
It's going? Oh, it's good. It's going nice and slow. You can see that the dispersion, and basically we're looking at a 30-second window here as we're going out in range, so we're at 2,000 kilometers, that the dispersion of mode 1 in the case where there's a SOFAR channel is really insignificant, but we get this really strong linear decay, or linear, I guess, decrease in propagation speed for the Arctic channel. And there, as soon as we hit about 5,000 kilometers, we start to get interaction with the shallow water, and that kind of condenses the higher modes. So I want to focus here on mode 1 because that has that characteristic. And here now, going all the way out to the station, we can see that we have this essentially linear dispersion occurring at the Crozet Island station, and a vertical kind of undispersed mode 1 at the Ascension Island, with a 6-second delay from the first detection at the Ascension Island and an 18-second delay at the Crozet Island. So what we can do is we can take our signal here, and now this is only with one hydrophone. We could do such a ranging, and we can just overlay and find out at what distance would that match the dispersion features most closely. So then you have, if you had now 3 and you had a bearing, you can actually find to a rough degree with a single hydrophone where you would be. Now that's not probably good enough for what we're trying to do here at CTBTO, so we can actually look at more of the actual precise timing that we get from these cabled arrays. Some caveats on here, though. The modes are not always identifiable, and the group and the phase speed is greatly affected by the bottom proximity, so you need good bathymetric maps. An example here, there was a depth charge that was used and actually did help in some efforts to reduce uncertainty in models that was deployed 2 weeks after by the Argentinians. And when you look at that signal, it looks pretty similar, but I don't see that strong line. The dispersive characteristics are good here, that's what I'm showing, but we don't see that strong mode 1. That could be in part because the depth of those 2 events likely were very different. One was near the surface, where you're going to have lots of modal excitation of all modes, while if the other one was deeper, there's a good chance that you're going to be exciting the lower order modes. So what can we do with precise timing here? So this is the basic idea of where we are seeing those long elongated ellipses with just 2 stations. If we form an isochron, or a surface of equal travel time that doesn't have really any of the directional information coming in, we form 2 circles here, and where they intersect is where the source would be. And so based on not knowing where the source time is, they will intersect somewhere along that line here. And as soon as we are able to include a 3rd station, we can then pinpoint a spot. So we want to model now these refracted paths to form a virtual station, get a third station when we only had 2 physical stations there. And so the isochrons are basically going to be perpendicular to the path of the energy. And so geodesics are actually quite fast and easy to calculate, and they do represent that direct path of energy. And what we can do is essentially apply those the group speeds that we had calculated along those paths. And then the modal rays are something that's allowed to refract, are actually a pretty good way to model this refraction process. What I'm plotting here in the color is actually the phase speed, and that's to keep continuity of the wave fronts. If you have a gradient at the phase speed, the waves have to turn. So they're turning away from the continental shelf. So here, just to, and maybe this will play here? Okay. To show basically, if I now put a suspected event time of when it happened, and I trace where those isochrons are intersecting, you can see that they form a triangle because they don't all align at the same point. So what we're looking for is when these 3 isochrons intersect, it just happens that as things should work out, it does intersect at where the source would be. And this is, now of course, we have to put some uncertainty in there and how well I identified the features in the signal, and also what my ocean model is, but those misidentifications are really on the order of seconds and maybe 1 second, and very small fluctuation in meters per second. So we're talking about air ellipses that are not very big when you can get multiple stations. So just to kind of end here, bringing it back to, let's just say this was a small amplitude event relative to a nuclear explosion. And when, whoop, could you play that video? When we look at the wigwam test here, and this is a paper from Monk back from 91, he has had a recording. I don't think this had ever been digitized, so we can't get any more of that data. At least another colleague, Brian DeShaw, was not able to get that. But you see that big explosion here. It made a long signal for 4 hours, which is bouncing around the Pacific Ocean here multiple times. So almost a receiver anywhere in the world would be able to hear. Maybe not in, it has to be in the ocean that the explosion happened, I'll say, is maybe one caveat. But it looks like we do have a system that can definitely record nuclear explosions. And there is potential then, kind of doing the source localization, that if there are impulsive natural events, we could actually potentially do this with historical, natural or at least historical events like sus charges, and actually build up a database of to do tomography and confirm how well our models are. I'm showing 2 ocean models here, the World Ocean Atlas, and then this space-based ocean state estimate, which is actually using satellite data and fusing that with Argos float data to get actually some of the small-scale variability. So just to summarize here, propagation modeling is actually really important if we want to improve how we can localize events. And it doesn't have to be that complicated and computationally expensive. Basically, the 3 things that I showed here, if we can identify the dominant modes in the signal timing, then you can range via dispersion. And you can also use these simple mode modeling techniques to construct virtual stations from 3D arrivals. And yeah, I'll leave it at that, but
Okay.
Any questions, yeah.
Thank you, David. One quick question. Tarun.
What was the time width of the explosion event? Was it an impulse or?
It was an impulse. There was some talk of the Kepstrel analysis of being like a double impulse on the order of like a half a second, a little bit less. So it was very fast. My resolution of my spectrum there is wider than what the impulse would have been. So from an impulse that's less than a second, you still get 30 seconds of dispersion when it goes 8,000 kilometers.
Okay. So you have to be able to resolve the modes, right?
And that dispersion actually helps you resolve the modes because the modes have different group velocities.
Right.
Okay, very good. Thank you. Thank you all for attending the session. Yes. And so don't forget to look at the posters too that were talked about if you haven't already done that.
Yeah.
Thank you.
Peter, I need to go back to the office. So do you mind if I work with Bruce at 3 to 4 and then 4 o'clock you can see, check with him and then send it out to the, because Peter has to go to the posters between 3 and 4.
I'm allocated from 3 to 4.
Yeah. I leave and then you send it and yeah, is that okay? Sorry.
Hi. So do we switch names or? It's not. Okay. Okay.
Because it wasn't provided, and of course we can only work with the stuff we have, right?
Create one. Okay.
This is missing.
The first one is missing.
Only you have this, or you have
The rest we have.
So, okay, and for the poster preview, they are all uploaded? Okay.
We already
I have
received our poster, the notes, which
Oh, okay, you got.
these are the ones we have.
Okay, perfect.
the number of the.
Yeah.
The first is missing.
We just don't know who it is.
What?
But it will be possible to upload his presentation? If he's here with a presentation? Okay. So, can I get, I will call him right away if you don't mind.
That's a problem.
So that's Thursday. This is, oh, 1.4.
This is. Okay.
Do you want to call him? Maybe
Yes,
see if he's
the
here.
first. Okay. Good afternoon. This is the last session of the term, the Earth as a complex system. The first presentation is Ben Norin. Is here Ben Norin?
Yeah, do you have your presentation? It was not uploaded.
He has the presentation?
Yes,
He's not in?
yes.
Oh,
Okay, we okay?
okay. The presentation is atmospheric event energy estimation based on seismic data. But the presentation is missing, and we can.
It will be uploaded. Is it?
We must initially with the
So we keep the same order. Rittersaal, yeah. Are you the first speaker? The third. Okay, and have you uploaded your presentation? Okay, that's perfect. Okay, okay. We will start. Okay, so everybody will be there. You need a glass of water?
Okay.
Hopefully it's okay. Good afternoon. My name is Yochai. I'm from the Israeli NDC. And in a way, I'm going to show something that probably many of you know. It's mainly to show the concept of that we are thinking And in a way, I will be appreciating if somebody will come and say, oh, don't do it, it's an end, it's a dead end, and forget about it. Or on the other side, it might be like, yes, it's really interesting. And there are many, and I'm apologizing in advance because there are many works on that, so if I forgot people, it's not because it's my memory bad, and there is too many works, I'm not going to quote all of them. So this is a talk layout, and we saw this picture so many times. And what is our motivation? At least we are supposed to be, I'm reminding, this is our roast, this is what we are going to do. We are supposed to do monitoring, and we are tend to think about underwater nuclear explosion, underground nuclear explosion, but we have infrasound and we have atmospheric nuclear explosion, and although I hope that the last one was in 1980 and probably, hopefully nobody will do, we still have an infrasound, we still believe that somebody can do it, so then we need to monitor it. And at the end of the day, all this verification, and I think that it was interesting to hear, I think it was yesterday with the debate, the verification regime, this monitoring regime, at the end need to identify events that might be of interest to do on-site inspection. It's not only to identify and to say, okay, everything is fine, we know exactly what is it. And for that we established the monitoring technology, 4 technologies, and from the beginning we understood that it's not restricted, it's not seismology, it's only for underground. Infrasound will be for atmospheric, and probably hydroacoustic, we had an interesting talk, will be for underwater, and that's it, and there is no, I think life is much more interesting, and we're seeing lately that people start to understand that we need to treat all the globe together, so energy is moving from one media to the other, and we have a lot of works that we see today of infrasound detecting earthquake. We see passage. It's always natural to see passage between sea, underwater, and ground. The right direction. And only to remind you that, and one of the problems with this, and this is going to data fusion, and there is the layout that the IDC always shows, and taken from the IDC. We know that seismology takes seconds to minutes to detect. Hydroacoustic, it's seconds to minutes, and infrasound starts to be minutes to hours. And radionuclide, which I will not touch after it, can take between hours to days. So first of all, it's hard to combine them, all of them, and each of them can contribute some aspect to understanding of the event. If we look on the network, today, when I try to see what I'm doing and to understand why I'm bothered to think about measuring things from infrasound on seismic, the first thing that I looked was the typical distance of stations in the network. So if we are looking about distance between array, the minimal distance between infrasound array will be 11 degrees, 1,000 kilometers. And then naively you think, okay, then, and you can see the distribution, but then naively you can think, okay, this will take half of it, and this will be the time that you will detect something, the first detection in the infrasound. But actually what we really need to do is to do some grid of points on the globe and to see what is the minimal distance between each of, what will be the average minimal distance of a point on the grid to a station. And this will be the first detection. And actually we need 3 detection, but I stuck with this first, with the, so yes, always you have a station that is nearby the one point of a grid. So you have always minimal grid of 0, something almost, not always, but if you look on the average, you have 12 degrees. So it's something like more than 1,000 kilometers, and if you naively take 330 meters per second, then it's something like 4,000 seconds, something like an hour before we will have something. If we look on a primary station, it's almost the same distance. But now it's 600 seconds. So the first arrival we will see something 10 minutes after the event instead of 1 hour. And if I will succeed to know it then. If we include the Seismic Auxiliary station, then the situation is much better. We are now on 400 seconds. We will have something. So for me, although, and we heard it more than once, it's not something that the organization try to identify or to fix. The yield of the event is not one of the parameters, or the energy of the event. But I think, at least I know that immediately when something happened, the first question was, what size is it? In DPRK, and especially if we think about the last DPRK event, the size was very important then, because it moved you from one thing to another thing, and understanding, I think it's not complete. And sometimes the size is important because above some size you start to, at least in our thought, it's not anymore doable conventionally. You really need to move to a nuclear device. In general, I know it's getting better and better, but the estimation of atmospheric energy from a barogram is a little bit, it's poor compared to the poor estimation of a seismic energy. One of the reasons that, and you know it better than me, that the atmosphere is time dependent. So the velocity, everything can be changed. You need, if you really want to pin out everything, you really need to know the winds, you really need to know the atmospheric situation. Sound propagation for the Earth model is almost not time dependent, at least for our period of life. And because it's faster, if we can assess via signals that are going through the Earth, we might be in a better situation. Now, the theory behind it was already in the 50s. Papers by Ben Menachem, Pomery after it in 63, Ben Menachem was 64, there were even before. And lately there are by Rogers, by Kitov. People looked on that and analyzed things like that, but most of the cases it was done per special event. And what I'm trying to do, we're trying to build a method that we can implement it in a routine. The idea is that, as probably you know, there is the explosion. There is a shock wave at the beginning, then it's coming to be a sound wave. In the area, in ground zero, it can be, you will have some energy transfer, it will be P and S. If you have a good condition, you can create surface wave, and they will survive further. It need to be, it really depends on the last layer of the Earth, because the velocity should be the correct velocity. You need the velocity that will be comparable. It need to be a little bit near the sound, but not the full condition, and the theory is solved. The main problem is that it can be induced, the surface wave can be induced not only in the place of the explosion, they can be induced near the station, they can be induced in the between the station and the event, and the only thing that can help us is the timing. So if it is induced near the surface, it will take it the sound wave time to arrive to your station. If it's being produced near the ground zero, it will take the 3 kilometers per second for surface wave, around something like that. So this can help us to distinguish. So we are assuming that we know the location. The height is unknown, but the height is less than the distance that we are measuring. So now, instead of measuring the atmosphere and being dependent on the atmosphere from the event up to the point that we are measuring, the effect of the atmosphere is limited to the height, and then it's entering the Earth. Saying that, we are replacing something unknown to other unknowns. So it might be that we are not gaining anything. I hope that we are. So, 5 minutes. Oh. So I will be almost finished. The idea is to do it in 2 stages. Learn how to estimate the energy from the seismogram. You can choose whatever you want. I'm trying to do it or by Kanamori or by something like Coda magnitude. Take it back and then assume that this is underground explosion or something like that. You have some yield equation, but then you need a factor, or the other part, what is the connection between the height and the energy efficiency of introducing into the ground. There is an example, Pomory was reading it, giving a table. This is on MB. I wanted to do it on a surface wave, but he gave a table that says, okay, if you have a 20 kiloton, how you will measure what will be the magnitude if it's 10 kilometer height, 1 kilometer at the surface and below. And I used the Sika relation in order to look on the yield to reverse it. And you have something like, we can have something like a factor. If you're measuring a magnitude, what will be the yield that we are expecting to have? So I will rush it. People already show it. I will not try to say the full name, but in Ural mountain there was a meteorite, and it was measured. And lately, several interesting papers were dealing with that and showing that surface waves was recorded really all over the globe. Those are 2 examples in BFVR, and unluckily there was an earthquake nearby, and you can see the overlap, and the lines are representing the Rayleigh wave and the lava wave that can come. Again, in Kirk, you can see the distance and the azimuth from that, and I think that there is a clear sign. Another example is the last Chinese nuclear explosion, 1 megaton. I was surprised to see that you can retrieve data for that, which was very nice to understand that suddenly there is data and probably there are more. We are only starting to investigate. And again, there is very nice seismogram that you can download from IRIS. This is 1 station. Those are 2 stations. You can see Canoe, you can see N2. Very nice signature. So we can measure it. I did something very naively, only to show what we are thinking on. I took the magnitude that was reported for those 2 events. And again, this is not the magnitude that I want to measure. I want to measure the MS. And this was the MB. And naively, you are getting that the event with magnitude 3 will be something like 18 kilometer at 18 kiloton at 10 kilometer. And the other event will be something like 1.5 megaton if it was 10 kilometer height. The estimates for the Chinese was something like 1 megaton, between 151 to 1.5 megaton. The Oral was at 30 kilometer, it was something like 4 to 500 kiloton. I don't have anything, I didn't yet calculate this height, and probably we can do it theoretically. So in summary, I think that although it's we are replacing unknowns with unknowns. And in a way, it's like you're saying, okay, I will feel very comfortable to say a standard underground nuclear explosion would be at the same, this will be the yield. And then to come to somebody and say, please do the theory and try to, theoretically, because it's even, the equations are there, how to do it. If you take back Menachem book, chapter 11, you have all the equations, you only need to do the propagation. but we will have always the ambiguity of saying, if we don't know the height, there will be a trade-off. But we can give some threshold. We can give upper threshold and lower threshold, because we can say it's not more than that and it's not less than that. If we detect something, we can say, okay, it's not less than the assuming that this is underground explosion. This will be the bottom line. And if we don't see anything, we can say it cannot be more than, unless it's very high. Thank you very much.
One question.
Okay, maybe time for one quick question. I have one, if nobody else.
I thought what I said.
Do you have a database of events that you can use to validate your different estimations?
This is one of the main problems, because in order to calibrate your station, you need data set. I'm actually very enthusiastic after I saw some of the talks here, and I learned that, yes, there is some data that you can take from the old station, but all events are terrible because they are very nice and you saw it, but you don't have the station for that. They are not existing anymore. I think that even only in the last debate that we saw, there was the JPL with all the meteorite, and I'm really hopeful that, actually I'm more enthusiastic than before, because suddenly I realized that it might be that we have more event there than we think that so we have better calibration chances than I thought at the beginning.
Okay,
Thank you very much. So thanks again.
The next presentation, I call to Focus. Fox is here? Yes? Okay.
No, that's the wrong one.
Complex propagation.
It's the 1515 rotation.
Okay. Well, I'll take the calls. Difficulty.
Yeah, that looks better.
Okay.
Okay, welcome to my presentation with this very complex title. It's about a chemical explosion that occurred in southern Germany last year. And it is only possible thanks to the interaction of the atmosphere with the solid Earth. And I think it nicely ties to the previous presentation, because it's one of these examples where we actually try to investigate an explosion that occurred just above ground, so kind of in the atmosphere, with seismometers only. This is what happened. In the morning of September 1st in 2018, there was a huge chemical, or probably chemical or petrochemical explosion on an oil refinery site in southern Germany. So this is where it took place. It's close to the town of Ingolstadt. And the blast was audible in this Ingolstadt, which is 10 kilometers away from the explosion. And newspapers report that there were broken doors and windows even in the neighboring villages at more than 1 kilometer distance. So it was a quite significant explosion. And according also to the newspapers, likely what happened is that hot petrol escaped through a tiny crack from a highly pressurized reactor, and then occurred the explosion slightly above ground. This is the data we have available. So all the triangles you see on the map are seismic stations, seismic broadband stations. There's not a single infrasound or pressure station involved in this study. The black triangles are all the permanent seismic installations from the national seismic networks, and you see there are quite plenty of them. And we had the nice occasion that, in addition, there were plenty of temporary broadband stations in place thanks to the ARCA seismic network. So these are all the red triangles. And they nicely cover the Ingolstadt explosion with a distance of 40 kilometers between two stations. So overall, we had 400 seismic broadband stations within 400 kilometers from the explosion. And this is how the data looks like. It's not so nicely seen on the big screen here. It's all of the stations, all the record sections, all the traces just plotted on top of each other. Only the vertical component, no pre-selection, but 1 to 2, like a rather narrow bandpass filter, 1 to 2 hertz. And what you can see clearly are here the seismic phases. So like P and S or some regional phases, they travel with like 5.5 to 5.9 kilometers per second, and a bit slower for the S waves. And the amplitudes here, they correspond to a seismic event of local magnitude 2.0 roughly. But more interesting for us somehow was that we also see acoustic phases, and these are the three here. So what I term phase 1 is this down here. You can see it in distances from 10 to 200 kilometers from the source, and it, I have to stand here a little bit, and it travels with celerities, so that is just distance by travel time, of approximately 310 to 340 meters per second. There's a second phase visible here, and you can spot that all the way from 150 to 325 kilometers away from the explosion, and it travels at slightly lower celerities, 270s to 300 meters per second. And there's a weak third phase, somewhere hidden here. It's really badly seen on this type of screen. It's better on screen and in the paper. And you see that between 250 and 350 kilometers from the source, and even slower with celerities of 240 to 260 meters per second. And all in all, these are 84 positive acoustic detections on the seismic stations within 350 kilometers from the source. And I should say that this number only holds if you apply like a signal to noise criterion, that it should be 3 times as much as the maximum noise. So this is like a zoom in on the waveforms. I would be very brief on this. On the left, you see the seismic waveforms. They're kind of complex as we expected, 10 to 20 seconds durations. On the right are the acoustic waveforms, or I should call it seismoacoustic, because still it's a ground motion, but it's induced by the acoustic signal. Most of them have much simpler waveforms, as you can see here. Shorter in duration, maybe 5 seconds. And yeah, sometimes it's more complicated, like here. Or there's even some uglier ringing, obviously, of the sensor here. Which tells us already that from station to station, obviously the seismoacoustic signal will look much more different because of the coupling from atmosphere to solid earth, which is potentially very different for each of these sites. If you zoom in, the seismic signals show nice upward first motion, as you would expect it for an explosive and an isotropic source. The acoustic signals, again, they seem to be a bit obscured by this seismoacoustic coupling from air to ground. Sometimes it seems like there's some upward motion, but actually on several stations there's clear downward motion. And this is what I would expect if the pressure airway is actually arriving from above and coupling it to the ground. So I was thinking, with so many stations available and such a nice spatial coverage, maybe I can get a feeling of the attenuation of the infrasound signal. So I plotted this. What you can see here is actually not the pressure amplitude, but of course the ground velocity amplitude, because we are only using seismometers, versus distance, the maximum amplitude of the seismoacoustic signal. And so caution, this is not just air pressure, but it's actually ground motion. And the relation between air pressure and ground motion, we don't really know, and it could be highly site-specific for any of these dots. The triangles are the temporary installations, and the circles are the permanent seismic installations. This is important because usually the permanent seismic installations are way more carefully installed in solid rock formations and carefully shielded from any external disturbances. You don't want these. But the temporary installations are not. They're like near surface and not so well shielded. So they are potentially much more sensitive to the pressure perturbations. And this is also what you see here, that some of the highest signals we see, those up here, they are from the temporary stations. And at the same distance, the permanent stations show a seismoacoustic signal, which is like 2 orders of magnitude less. Still, even though there's big scatter in this, would think that within 200 kilometers from the source, you very roughly see that the amplitudes attenuate approximately by a factor of 10 per 100 kilometer. And maybe this, if you understand all this coupling better, maybe this can give you some insight into the attenuation within tropospheric ducts, because all of this is within the tropospheric ducting range, not the usual stratospheric one. And yeah, it's significantly less that you would expect simply from geometrical spreading and attenuation. So why did I call it complex in the title? It's because of the spatial pattern where we actually detected those signals. And let's walk through the different phases. The first picture on the left is for what I call phase 1, which is potentially tropospheric ducting of the sound. We mainly observe it to northwest and southwest of the explosion, so everywhere here, and a little small narrow corridor to the north. The second phase was potentially stratospheric guided waves. We see them in the north, up here, and also to the west, but pretty much nowhere else. And then there's phase 3, which is potentially thermospherically guided waves or reflected waves. We see that in a broad azimuth range from north to east, but nowhere else. Note that there's like a station gap here and here, so we don't really know what's going on there. So if you put it all into one picture, this is how it looks like. So some detections here, here, and there, but everywhere else there's pretty much nothing. So let's confirm this using 3D acoustic ray tracing. That's what people usually do with infrasound. Oh shit, okay. So what did we use? The GeoAC ray tracing suite to model everything, the ECMW of atmospheric model for 3 o'clock, the explosion was at 311. These two models to extend it to higher altitudes because we potentially have thermospheric arrivals. And this is how it looks like. So in the background, in color, you see the effective sound speed. And the red rays on top is where you should expect the rays to bounce back to the surface. And this is an example for southwest of the explosion. So what you can actually see, it doesn't predict any stratospheric arrivals, so there's nothing bouncing back in this distance range coming back from the stratosphere. It does predict rays bending back from the thermosphere, kicking in at like 250 kilometers distance. And if you zoom in very closely into this box, this is the picture down here, you would see several very shallow tropospheric reflections, up to maybe 80 kilometers from the source. So again, if we plot it all on a map, this is how it looks like. The color switch now, we're no longer looking at amplitude, but at celerity. And again, it's a very busy plot. All the big symbols are our detections. All the small dots here are the bounce points predicted by the modeling. So let's walk through phase by phase. Again, phase 1 is in fact shallow tropospheric guided waves. All of these here, it generally matches kind of well. All of these have very shallow churning heights. And, but, however, our detections extend way further to the southwest than modeled. And also this corridor of detections to the north is not at all reproduced by the atmospheric model and the ray tracing. But there's some data from a weather balloon available from somewhere here. And if we use that one, we can actually create some reflections to the north. So these are probably likely to small-scale variations which are not included in the ECMWF model. Most notably and most strikingly somehow, there's no stratospheric reflections or refractions predicted by the atmospheric model and the ray tracing, but we do see them quite prominently up here and here. So why is that? I really don't know. Last but not least, phase 3 could actually be potentially thermospheric reflections. They are also predicted by the ray tracing, but they are predicted all around. We only observe them somehow here. Plus, our observations are closer to the source than actually predicted by the model. They are further out here. There's one nice feature, though. You cannot, well, yeah, you can see it a little bit. As you can see, the modeling says that the closer you are to the source, the lower the celerity is, and the further you go away, the higher it gets. And actually, that's something that we do observe in this bunch of stations here, for example. So the closest one actually records the slowest celerity, and the further you go away, it increases a little bit. So this makes me somewhat confident that the detections actually are thermospheric detections, seismoacoustically measured. So this would be the summary. Yeah. So we have this long-range propagation of tropospheric rays in this direction at very shallow altitudes. However, such shallow heights and where the rays are predicted to bend down, they are on the limit of the reliability of the ray tracing approach. We have these detections up here to the north, which are likely due to small-scale variations in the atmosphere, small-scale anomalies, maybe close to the source. And obviously, the ECMWF and the ray tracing cannot really account for this. Plus, maybe we have these nice thermospheric detections. And they're rarely observed because the signals are strongly attenuated up there in the thermosphere. So this would be among the first large-scale, in spatial scale, detections of really seismoacoustic detection of thermospheric rays. So this was the discussion about the stratosphere, but again, I have no time to discuss it, so this is the summary. The alpha-ray seismic network resolved the propagation of seismic and acoustic waves generated by this chemical explosion in great spatial detail. It shows you how nice it is to have a sensor every 40 kilometers. And this dense spatial sampling may allow insight into the attenuation within tropospheric ducts. Well, there's this caveat that we don't really know the seismoacoustic coupling. And yet, small-scale atmospheric variations likely had strong effects on the infrasound propagation in this case, so wave-based modeling rather than this ray-based modeling may be more appropriate. And actually, we now plan to equip all our broadband seismic sensors with additional infrasound sensors to finally know which is actually the sound signal and which is the seismic signal and how the two connect. And I should say, if you have any good idea what else should be done with this data set, please come and talk to me. I'm very open on collaboration and to do more on this. Thank you very much.
Any questions? Okay, I have one. The meteorological condition over this area, were they kind of uniform? I know you mentioned there was a storm, but for example, for the thermal structure of the lower troposphere, do you know what it was? Because I forgot, what was it, early morning?
It was early in the morning, yes, at
So
5 o'clock local time.
So there might be an inversion?
I mean, it looks like there was like some inversion at very, very shallow heights, but there was almost no inversion and very little winds up in the stratosphere, yes. This I know. And otherwise, I mean, it's all based on the CNWF forecast model in 3D, so, but.
Okay, thank you very much.
Billy, his presentation, modulation of gas fluxes at the soil atmosphere interface due to couple physical, chemical, and biological effects.
Thank you very much. So indeed, it will be a very different type of coupling between the geosphere and the atmosphere. My presentation is, I would like to show you that indeed gas fluxes at the soil-atmosphere interface are modulated due to couple physical, chemical, and biological effects. Please note that this is the work of my PhD student, Clément Alibert. First, this study is made in order to better understand seepage following an underground nuclear explosions. So first, some gas is produced, including radioxenon in a nuclear cavity. Then comes the gas migration moment with advection diffusion in unsaturated fractured porous media under pressure and temperature gradients, leading possibly to seepage. Then comes the atmospheric transport, leading possibly to detection. However, due to radioactive decay, dilution and modulation of gas fluxes, as well as fractionation of elements and isotopes, the 4 isotopes of interest in the atmosphere, total activity and ratios, are not the same as the one in the cavity at time 0. And the evolution is difficult to render with models because some of the processes are not well known or well taken into account. Therefore, discrimination may be a little bit tricky. Today, I will focus on the seepage at the interface between the soil and the atmosphere. The soil-atmosphere interface is not as simple as usually thought. Indeed, this is a boundary layer made of rock, water, air, which means multiple gaseous components, and it contains microorganisms and plants, at least the roots. If you add some rain, barometric pressure fluctuations, or other type of meteorological events, we are left with a highly dynamical and heterogeneous system with variations in space and time of the water content, pressure and temperature, gas permeability and porosity, as well as biological activity. So the question is, what are these effects on surface gas fluxes related to a deep gas source? To answer these questions, we carried out some controlled tracer gas injections in soil columns in a climated chamber. The soil column is 60 centimeter high, and it is filled with a simple modal soil consisting in silica sand, pure silica sand. The controlled conditions are constant temperature and humidity, automated watering, diurnal light cycles, 12-hour daytime, 12 hours nighttime, and the barometric pressure fluctuations are natural. We injected some SF6 at the base of the column with a constant flow rate. And we used one column with plants, seeded with a common type of grass, and another column was taken without plants, and it is referred to as the control column. We conducted a long-term and high-resolution monitoring of the injection overpressure at the base of the column, SF6 and CO2 surface fluxes at the top of the column, and the changes in the water content in the entire system. Here are some observed SF6 fluxes following injection in our soil columns over a period of 3 months. You can see in green the data for the column with plants, and in black data for the control column. SF6 was here injected at various concentration and flow rates, and as expected, gas transport occurred by advection dispersion in response to the injection overpressure. Also, we have to take into account tracer solubility in water, as indicated by our model, which fits reasonably well to the data here, as shown in red color. And this model includes advection, dispersion, and gas solubility. We will now focus on this period of time where SF6 was injected at a constant concentration and a constant flow rate. Here first, we will have a look at the water content during the same period of time, the water content as a function of time, for the 2 columns between 2 watering events. First, evaporation occurs in the control column at a constant rate, and in the column with plants, evaporation is a 2-way process, a 2-stage process, with one is being evaporation, physical evaporation during nighttime, the other one being biologically driven water evaporation, also known as transpiration, during daytime. Transpiration rate is twice as efficient as evaporation alone, and therefore water content in the plant column shows fluctuations controlled by daytime lighting. Here is now the SF6 flux in the control column in black again, and in the plant column in green. And first, watering was responsible for a sharp decrease in the flux observed at the surface, followed within half a day by a significant increase of the flux due to transient overpressure and preferential flow. Then comes a slight decrease of the surface flux due to evaporation in the control column and evapotranspiration in the plant column. And finally, we can observe similar decrease in the SF6 flux in both the control column and the plant column, and this happens at the same time as an increase in the barometric pressure. From this observation, we can derive that gas fluxes are controlled by pressure gradient and gas porosity, in turn controlled by water content, either infiltration or evapotranspiration, as well as barometric pressure fluctuations. We will now focus on these second-order variations that are seen only in the plant column. So here is again this SF6 flux during 2.5 days in the plant column only, and I'm now presenting the CO2 flux that is measured on the same column. Remember that SF6 was the only tracer injected, CO2 was not injected, CO2 comes from the biological activity. We will need also to see what happens regarding the water content in the columns, here shown in blue, and also about the pressure gradient, here shown in pink. I will separate what happens during daytime and what happens during nighttime. So during daytime, we observe a decrease in the SF6 flux, as shown by the green arrows here, and at the same time, we can observe negative CO2 fluxes, which means plant photosynthesis, as shown in these chemical reactions. CO2 plus water gives oxygen plus organic matter. At the same time, there is a high water loss by evapotranspiration and a decrease in the pressure gradient. This goes with an increase in the gas porosity and leads to transient gas storage. So altogether, these processes are responsible for a decrease in the SF6 flux observed at the surface of the column. During nighttime, we observe an increase in the SF6 flux, which is correlated with a positive CO2 flux, which means plant respiration, which is the reverse of the previous chemical reactions, this time consuming oxygen plus organic matter, giving rise to CO2 plus water. At the same time, we observe a moderate water loss by evaporation alone, physical evaporation, and the pressure gradient is remarkably constant, as shown by the horizontal pink arrow. This comes from the fact that CO2 produced by respiration has a higher solubility in pore water than oxygen, which decreases local pressure and increases the pressure gradient. So altogether, this explains the increase in the SF6 flux. As a conclusion, I hope that you are now convinced that gas fluxes at the soil-atmosphere interface show a large dynamical response, controlled first by barometric pressure, second, water content, and third, plant metabolism. Biologically driven controls on gas fluxes accounted here for about 10% of the variations observed, but they could be more, they could be higher for larger biome, because here we only use small grass. This biological control is twofold. One is evapotranspiration by plants, which controls water budget and gas porosity and pressure. The other one is respiration by plants or microorganisms, and is responsible for oxygen consumption, CO2 production that drive important pressure changes due to contrasted solubility in water. This has important consequences regarding detection of underground nuclear explosions. Regarding on-site inspections, we have to be cautious on high space and time variability for one-time gas collection. And regarding international mooring system, modulation of radioxenon released to the atmosphere must be taken into account by atmospheric transport modeling. Our ongoing modeling effort will provide further quantification and prediction. I thank you for attention.
Thank you very much. Very interesting. Any questions? Yes.
Thank you. Very nice presentation. In your soil column, I mean, that was quite a small volume of soil you used here. Have you kind of scaled the grain size of the material you have, or is it just normal as you take it out in nature? I mean, is it normal soil material you use?
The soil has been sorted. This is pure silica sand. This is 200 micron, very well sieved. So it's a model soil. So this is something we know very well. It's been used for many, many times for agronomical study.
Okay, we have time for one more question.
Good presentation. Eric, was there any evidence for preferential flow in your experiment? Or are there any issues that we should be thinking about in that regard?
So, thank you, Charles. There is evidence for preferential flow. An example here, for example, is after a watering effect, which could be a rain event. We have almost no gas flux to the surface, of course, and sooner or later you can see that the gas flux is a little bit enhanced to what it could be, and we attribute this to transient overpressure and preferential flow across the waterfront. Because of course the injected gas has to go through the water, and as you could see on one of my slides, the overpressure was not very big. It was on the order of 20 millibars.
Okay. Mike, please.
Thank you, Eric, for your presentation. I'm Robin Riedman from CTBTO. Do you have any spatial resolution on that? If there's any, I assume you just have one pixel, if you will, or did you do? Can you really see like where the preferential flow is and what the differences in SF flux might be over the surface area of your column?
At the moment, we only measure the flux in the central part of the column with this accumulation chamber shown here. So this is pretty much 80% of the surface of the column. But in the near future, we will have pressure measurement and chemical composition coming from every 5 centimeters here, because we change our analytical device for a much more powerful mass spectrometer with a very low flow. So now we could see what happens in the profile and not only from the top. And the first results show that there is a very strong channeling, so there is preferential flow.
Maybe follow-up question, do you also include nematodes or any kind of worms or which could cause preferential flow as well?
I didn't catch it. Could you say it again?
If you introduce animals, worms.
Worms, of course. But the root zone alone here is enough to have a preferential flow, because water is taken by the roots. It means that water is taken along vertical roots, and so water is away. I mean, these define channels, vertical channels, and it changed the permeability field. So the permeability field is no longer isotropic.
Okay, thank you very much. Yes, I will mention now. Okay, that's now is the presentation of the preview. Okay, now we will go to the preview, poster preview, and don't forget that it is important to vote for the best poster. So there is on your mobile phone you can access the little tool to do that. Okay, so now we will call the posters. Okay, call for poster 1. It's here. Please 9. Just line up in the alley here. You are the first. 1, 9 is here. 10, 12, 13, 15, and 16. Nora, please. You have 1 minute for. Okay, you have 1 minute. It will change automatically after 1 minute. So we'll start now. Thank you. The first BRL.
Good afternoon, everyone. My name is Rodrigo. I'm a physicist. And the aim of my work is to study the temporal and spatial variability of beryllium-7 in South America and in the surroundings of South America. For that objective, I have studied almost a decade of time series of variant concentration. This was provided in a BDEC collaboration. These are 9 stations that are very well distributed latitudinally and longitudinally. So what is novel about my work is I have studied this time series, removing the seasonal component of this series that is very strong in the mid-latitudes. So I have created an anomaly time series, and in that way I have compared this anomaly time series with climate parameters. So it will be very easy to identify me. Please come and talk to me.
Thank you.
Aldo Lab, the number 9.
Okay. Number 10. Okay.
Good afternoon. My name is Bob Woodward, and my poster is a relatively qualitative look at interactions amongst Earth subsystems based on using the EarthScope Transportable Array, which is a very large seismic network currently deployed in Alaska. The basic idea here is large, high-quality seismic networks are excellent tools for understanding interactions between the Earth's atmosphere, the hydrosphere, the cryosphere, the magnetosphere, and those interactions with the solid Earth. The key is that the signals from these interactions are often very small, so you require really uniform networks, low noise, long duration observations, and diverse sensor suites. So this is a characteristic of the transportable array, but also applies to the International Monitoring System and the Global Seismographic Network and a number of other networks we've heard about this afternoon. The key benefits are that you improve the understanding of Earth's processes, which is important scientific, and you also understand better small signals for nuclear monitoring.
Thank you very much.
Good afternoon. My name is Daniela Ghica. I'm from National Institute for Earth Physics in Romania. In Romania, at 4 seismoacoustic array of 1.2 kilometers aperture is deployed in northern Romania. We use this seismoacoustic array to characterize the site detection background in terms of typical sources observed by both types of sensors. We studied the nonlinear interaction between ocean waves in terms of atmospherics, named microbarons, and crustal microseism, which could be detected at the station. And we identified three direction of arrivals, detections from North Atlantic, Black Sea, and South Atlantic. Thank you.
Thank you very much.
Hello, my name is Artemi. I'm from University of Vienna, Department of Geophysics, and I would like to invite you to my poster so you can see how thunder looks like on seismic stations. Because if you can hear it, you can record it. If you can record it, you can measure it. And as Flora and Fuchs mentioned, we have an incredible array of seismic stations in Austria, which is called ARRAY, and we happened to record a huge thunderstorm that consisted of approximately 60,000 separate lightnings. So welcome to my poster. It's really easy to find. It's like super black. Thank you very much. Ciao.
Thank you. Do we have 16?
Finished? Okay. Okay, with this, we finish our session.
Just one small announcement before. So the official poster presenter attendance time slot for 1.4 is today from 16:30 to 18:15. So all presenters, all posters, presenters are requested to be at their poster during that period of time. So thank you very much.
Okay. How are you?
Yeah.
You consider if some
Yes. Yes. Thinking about, I'm glad you mentioned. To me, presentation by Mr. Lee, transfer to the ground was really a big one. I don't know what you have in mind. Do you agree with this or?
But the problem is the first presenter is here and the presentation is not loading. And
Yeah.
So we'll always
Can't even start.
we can even start.
Where's the guy?
Yeah, I don't know. Should we say something? There is a small delay. We are waiting for the.
Yeah. Sound should be there though, because yeah.
So I'm sorry, we might start a few minutes late because we are still waiting for the IT support team to join us. So just a few minutes, hopefully.
Oh, I could say something about this.
Yes.
Yeah, dear presenters, poster presenters. Now at the end of this session, we will have the poster preview slot. And while it may be somewhat strange to have that slot after the poster session has finished, I think it's still a very good idea to present these 1-minute presentations. That gives you all a chance to see the posters. The posters are still hanging. So at the end, I suggest we all go to the posters and there's more chance to discuss. Also, we have a good number of posters, 45, of which we have 32 presentations loaded. So what we will do at the end is we will split, we'll invite the first 16 posters to line up and give their presentations, and then we'll have a short break and ask the next 16 presenters to come up.
Okay, so I think they are just loading the last presentation. So welcome to this afternoon session on the design of sensor system and advanced sensor technologies. As you can see in the program, there will be 4 oral presentations this afternoon, and then we'll have 6 presentations tomorrow morning starting at 9. As Klaus said, at the end of this 4 oral presentation today, there will be a posterior preview session. And so this session covered the design of a sensor system, and as you will see, so sensor system for the 4 IMS technologies, but also for a number of OSI-related technologies. And I don't... Okay, I think we are almost ready to start with the first speaker. I don't know if you... Yeah.
Yes, the first presentation, this title is Descriptions and Results from a Feedback Digital Infrasound Detector System, will be presented by Dr. Guralp.
Okay. And is there a point?
Well, good afternoon, everyone. This project started as a research project, and all I would say is that I was quite surprised not to be able to find any references on actually feedback infrasound sensors or detectors. I've searched quite hard, but certainly there was no reference that I could find. So it became quite a sort of an involved project. So I started really the project by looking at what can be achieved, very, very cost-effective way of making a reasonable infrasound detector, and looking at it as a cybernetician rather than a engineer. I felt that one can just look at the infrasound open-loop systems that exist, and that's being used by everyone so far. The detector is a very simple device. It's effectively there's a mechanics which is associated with the detector, and then there's a displacement sensor or any kind of sensor which could be a capacitive, whether it's a variable area or variable gap. It could be inductive or LVDT as a linear variable differential transducer, or interferometry, or for counting or fringe counting. There are so many different types. And it could also be acoustic or piezoelectric type detector, and also velocity responsive, which is mostly used in seismometers. And my surprise was that in 1970, when I started my work on seismometers, there were no feedback instruments really. And by putting feedback, one could achieve so much more from a very simple mechanical system around the seismometer. So in this case, you know, the mechanics could be quite complicated. One could use a bellow or a diaphragm, or you could simply use a 10-pound sterling speaker cone, which has a coil in it, and which has a wonderful suspension system. And the size is about, let's say, 50 millimeters to 10 centimeters diameter. And you can make a perfect, absolutely wonderful infrasound sensor without spending thousands. And the reason for that is that the speaker technology is there. It's a suspension system. It has a perfect area where the pressure can be exerted on. And the backside of this, of course, needs to be isolated from the environment. It has a coil in it, which is already manufactured for you, which you can apply feedback, or you can just literally have a reflector on it and measure its movement. But it has disadvantages. The very simple mathematical formula for such a device is literally a set of amplifiers and a second-order suspension system, which the resonance is shown there, and then it has internal damping or damping due to the reservoir that one can put at the back of the device. So moving from there, we chose, for example, a speaker setup which is only 40 millimeters in diameter, a fantastic device, and it has an aluminum cone which is rigid, free of quite a lot of resonances, unlike bellows, and it formed a very, very nice infrasound sensor by reflecting. One didn't even need to put a reflector on it, but we just put a an optical measuring device to be able to measure the displacement of it. So it is a simple thing to do until you look at the transfer function. And that the transfer function, and this is actually transfer function of a bellow that we have included in our design, in that it has a resonance. The resonance is there, and unless you dissipate or damp the resonance or do something to it, you're never going to get this instrument work satisfactorily. Unless, as I think most people seem to be doing, you cut off that resonance, meaning you put a filter, a heavy filter, and get rid of that peak. But whilst you might not see it during recording, the peak is there, and it's likely to saturate. And it doesn't have characteristics which can be, I should say, defended by any kind of sort of instrument requirements. The transfer function is easy to make it is also quite easy. And this needs to be removed. And this is the same sort of problem that seismometers had in 1970s. Now, moving from there, the thing that I'd like to do is that just to show the very simple difference between an open loop system, which is the transfer function, and the feedback system that you add onto it. It has lots of advantages. The complication here is the fact that you have a detector and you have, let's say, a displacement sensor, and you need to have a force transducer in order to apply feedback so that the force transducer brings the displacement back to where its normal position is, which is also known as force feedback, or it has quite various names to it. But most importantly, what you can do is you can also apply to that force transducer a calibration signal that open loop systems do not have, or could have, but with certain amount of further complication. In this case, when you've closed the loop, the overall transfer function is still, it's extremely simplified, is still a second order system. But you can see that to the resonance that we had previously, you add another component, which is effectively the gain of the system, including the feedback gain, in such a way that the resonance gets dominated, and you effectively extend the resonance frequency above the level where the resonant frequency is. Not only that, you can also put a component in here by literally differentiating the feedback signal, such that you can control the resonance, which is defined by the damping coefficient. In such a system, you can produce an output which is proportional to what I call pressure acceleration, rather than where I think most people are used to the actual pressure signal being the displacement of the diaphragm. You can produce the velocity signal, which you can get the same thing by putting a moving coil onto the diaphragm, or you can get the displacement signal. You can get all those three from one instrument by putting feedback around it, which is again very similar to a feedback seismometer. So this does have advantages. Not only the fact that I mentioned the calibration becomes a reasonable way to if you like, find the characteristics of the system. Now, going through, and this is not exhaustive, so to say, going through the different set of statements that you can extend the frequency response both in the high frequency and in the low frequency part of the response. It's literally by putting more gain to the system that you extend the high frequency, but you have to ensure that you can stabilize it and provide stable transfer function, because ultimately, as I was saying earlier on, the transfer function of the system is defined by literally a parameter which is in that position. There is no mechanics involved in that parameter. In the open loop case, the transfer function or the stability of the system is dependent totally on the diaphragm or the mechanics of the setup. It allows you to be able to calibrate it, and the calibration could be in any form of signal. You can either put pseudo-random numbers, or you can put step responses of sine waves, or you can even put the infrasound detector that you would like to see how the system responds back to the setup. You can measure the detector's distortion. I've never seen a distortion measurement made on an infrasound detector that the community actually uses. It's sort of almost avoided for reasons that probably is now going to become more apparent. More importantly, you can calibrate it, and the absolute calibration is available. You don't really need to go to any kind of laboratory to be able to calibrate it, because what you need to do is simply, as one does in seismometers, calibrate the feedback parameter, which is the force transducer. Once you know the transfer function of the force transducer, or its value in terms of amperes per meters per second squared, or in terms of the quantity that in infrasound might be volts per Newton, for example. Once you calibrate the feedback transducer, you effectively have calibration to the unit forever. It will not change unless your force transducer characteristics with changes, which is quite unlikely considering these days how magnets and coils are so stable. So there is quite a number of different advantages. Not only that, the system can become extremely cost effective, because even though you might have one extra transducer to feed back, you don't really need to worry too much about the mechanics, or the precision of the mechanics, or the tweaking of the mechanics in order to get your response. I hope this is all clear, but you're more than welcome to ask specific questions later on. Now, the other thing is that you can reduce the inherent noise of the system, because by modulating, by detecting, let's say, using a capacitor transducer, the displacement, you can modulate the capacitor transducer at a particular, let's say, high frequencies, maybe 10, 20 kilohertz, and demodulate it such that you move away from the flicker noise region or the low frequency noise region, or the noise region of low frequency amplifiers that one tends to use with capacitive sensors, such as the diaphragm on a capacitive sensor. So there are lots of advantages. Now, what I want to now do is literally go to the mechanics of it. And this is not the final instrument, but this is one of the things that we designed. We patented it simply because there is no feedback infrasound sensor. And just to discuss define the instrument, what we decided to do is to use a bellow. And the size is such that it became a research project, such that we decided to make it as convenient as possible for us to be able to work. There's a bellow, and the bellow is connected to a differential capacitive transducer up here. And in that chain, we decided to put, and we tried different types of force transducers. There is a magnet and a coil. So in here, we have a bellow, a rectilinear parallel spring, which is what I said, because the bellows are notoriously bad for modes of resonances, because the bellow will wobble in all directions, and different modes of resonances will be there. But we've decided to put parallel springs such that this device, there are two of them, one at the top, one at the bottom, such that this bellow, as much as possible, will move rectilinearly, meaning up and down, in that when the pressure is exerted or the pressure changes in this part, the bellow then moves up and down, and we detect it up here with the capacitive transducer, and then feedback into the force transducers with it there. So in here we've got a preamplifier, which is sort of a side view, and then the feedback board. And to that, one extra complication is that we can adjust the position of the transducer depending on the DC change in pressure. And that is, when you take it to different levels, height, different places, you would need to reset the center position of the device. And for that, we've put a motorized arrangement where the transducer is moved in such a way that we can zero it. So that is the basics of the mechanics of the device. Looking at it in real life, in terms of what it is, as I've pointed out, we have a bellow, which you can see from the side. The reason why I decided to put two pictures is that you can see the bellow there, which is side view. You can't see the parallel spring arrangement, but in there we have the force transducer within that area, which is also isolated from external magnetic changes. And then we have our preamplifier, the capacitive transducer is there, and the feedback electronics is there. You can see it's a sort of a prototype because we've experimented quite a bit with different types of electronics. Then we have a simple, okay, if we have a simple motor system which allows us to move this up and down. Now, the most important thing is that I have 2 minutes. Is that the feedback force transducer can be calibrated. We calibrated it, and that figure will ultimately determine the sensor response. Looking at it, when you close the loop, what you get is absolutely flat response from DC all the way, in this case, 200 hertz, and the transfer function is very well defined. Now, it's not limited to 200 hertz because one has to be honest. Here is the response which goes up to 500 hertz, but on the top of it, we have the open loop response, which is what I showed. This is the response of the bellow on its own. And once you close the loop, we can get flat response. That is the first mode of resonance of the bellow. It's horrible, but it's there. And then the third. The next slide is we can find the distortion of the detector in that we can apply a sinusoidal waveform. And the first mode of we can get the total harmonic distortion, which is actually 66 decibels, which is comparable to a good broadband seismometer. And this is a reasonably low distortion device in terms of response. Looking at the characteristics of the recording of the instrument, 2 instruments are put side by side in a lab, and I plotted the power spectral density. I haven't plotted the actual scale in terms of pressure in Pascal, but you can see the 2 sensors side by side. That's 10 seconds, 100 seconds. That's 100 hertz being sampled at 100 samples per second. They're virtually identical. If you now look at the longer periods, in this case, the sample frequency was at 10 hertz. You can go all the way down to 1,000 seconds. So in a way, we have achieved our desire to make a very, very cost-effective broadband infrasound detector. And thank you.
Just one or two. Maybe just time for 1 or 2 quick questions if you have. Okay.
What do I, what?
By feedback, what you don't understand.
What by feedback
Yeah.
is you measure the measurement you carry out, you feedback so as to you cancel that measurement in such a way that the force you feed back when you cancel the measurement is the measurement you make.
But you feedback, you come from outside, you feedback.
No, you come from the detector, oops, you come from the device that you detect, yeah?
Yeah, from the device you detect, you get it feedback.
Yes, and then you feed it back into the same device.
And it's correct, you
Continuously correct.
yeah, okay.
So it's force balance, yeah. Yeah? By the way, I started quite late.
Okay, no, we know.
Now we need to record it.
Thank you very much for this new developed infrasound sensor. Did you have a chance to compare open loop and the closed loop output signals?
Not really, because it's impossible to compare it, because there is continuously this resonance, yeah, which is nearly 30 decibels above. So all you will get is a buzz at 40 kilohertz, 46 hertz. So I have never compared it, no. But it's maybe something that can be done.
Two questions. The first one, you speak about absolute calibration. Can you be, sorry. You speak about absolute calibration.
Yes.
Could you be much more explain what is it really? Your point of view from absolute calibration?
Okay, what I call, I mean, there are all kinds of definitions of absolute. What I call is parameters that are readily available that you know accurately, such as you know the weight of a mass accurately. Would you say that's you know the measurement in amperes? Your multimeters are calibrated in such a way that they have absolute values. Yes. You can. So what in this case, what I have done is effectively. what I have done is that it was, in fact, in this case, the calibration was done with feedback. Because
but
you have
much more an electrical calibration, we can say.
Well, this is not electrical. So what I did was, okay, well, it's a trick of the trade. So what I did was, here you have an instrument which is running in closed loop. You zero the output. You then literally put weight on the bellow in such a way that you put, let's say, 10 grams of weight that you know to maybe 4 digits of accuracy. Then you measure the current that is fed back to the coil to retain its position, which means that you get a perfect weight against current relationship.
And did you try to evaluate your system with output pressure signal, reference pressure signal?
I haven't I don't have the facilities that you have to be able to produce an accurate pressure signal, but it will happen in the next phase, which I couldn't say.
Excuse me. I suggest that if you are interested, you have a kind of splinter meter.
Okay.
After that, because we are very short on time.
Okay.
Sorry for that. Okay, let's go to the next presentation. It is establishment of a network of political and scientific cooperation between CTBTO and the Great Lake region to contribute to sustainable development, and will be presented by Birimbiwari Nambogo.
This project has just been presented as introduction to the CYG challenge, but here we have only to show development. What is the problem? Many countries have signed and ratified the treaty, but are not actively participating in the verification regime of the CTBT. And this is a case of the Great Lake region countries. And why is this? The cause is normally the putting into effect of diplomatic relations. It is therefore important to awaken these relationships. The main question of this project is how to bring many countries to participate actively to the verification regime of the CTBT. Some of inactive countries face also two risk and natural disasters, such as earthquakes, volcanoes, and so on. And they may therefore need IMS data and IDC products from CTBTO to help them manage these risks. We thought that the installation of NDCs in such countries could be the solution to bring them to actively participate in the verification regime of the CTBT. And why? Because the NDCs serve as a diplomatic pole between CTBTO and the countries. NDC agents who can be trained can have to activate their governments to actively participate in the CTBT verification regime. The NDCs can have available IMS data and IDC products to help the government of the country to manage the disaster and the risks. The benefits for CTBTO, this project mean to awake the diplomatic relationship between CTBTO and inactive countries in the verification regime. The active work of NDC in the country will bring those governments to actively participate in the verification regime. That is to say, supporting the CTBT activities. CTBTO will contribute to sustainable development from the use of its IMS data and IDC products to manage natural or artificial risks in the country. Some specific SDG targets in the Great Lake region. Firstly, the Great Lake region has many natural hazards as seismic activity with a magnitude which do not exceed 7.0, but the geology and the weak construction in the region grow its vulnerability. Recent seismic events occurred in 2004, 2008, 2015, 2016, and 2017. Here we can see some pictures from building destroyed with the 2008 and 2016 seismic events in Bukavu City. And about the volcanic activity, the Nyiragongo 2002 eruption, 85% of the economy of the town of Goma in DRC were lost, and 15% of the geographic space of Goma was destroyed by the lava flow, as you see here. We tried to make some solutions that we can plan from the NDC if it can be installed. So defining seismic hazard zone, the PGA, peak ground acceleration, determination, seismic zonation in order to show the zones where the level of hazard is high, and structural analysis, coupling seismic data with the regional structural map for the determination of high-risk areas. So if we can have the seismic hazard maps, it will help the local population to know the areas at risk, as well as the level of the hazard in order to plan the type of seismic construction to be considered for the region. About the Nyiragongo volcano, which is very active in the region, contribution to the reports of volcanic activity of the Nyiragongo and the Nyamulagira volcanoes, and the population of Goma in DRC and Gisenyi in Rwanda and surroundings will receive support on volcanic risk prevention tools, which will help reduce information to the people using the NDC data. We planned some stations which could be recorded, as you see, 8 auxiliary seismic stations, 2 primary seismic stations, and 4 infrasound stations. In conclusion, the NDCs in CTBTO members country use IMES data and IDC products. The NDC are an important tool for the reinforcement of the diplomatic relations between the country and CTBTO. NDC can help monitoring seismic and volcanic activities in the region. Scientists at the institutions that will abort the NDC benefit from trainings organized by the PTS of CTBTO. These trainings are beneficial for the analysis of seismic and volcanic risks by local scientists. So, having a NDC well established in any country contributes to its natural risk management and make it visible to the international community, not only in political point overview, but also to contributing to science promotion. Involvement of young scientists through the NDCs is very relevant. The countries which have NDC can contribute actively in the verification regime of the CTBT. NDC provides expertise about using IMES data, build up national and regional capacities, in implementing treaty and increase participation in the verification regime. So such project could bring CYG members to search for young scientists from these countries and raise awareness about the importance of CTBTO and some benefits that they would have in using IMS data and IDC products. Finally, we are at the scratch, so we can say that it's a challenge in the Great Lake region. Thank you.
Any question from the floor? Yes, please.
Thank you for your presentation. I am also from the Great Lakes region.
Ah, okay.
Great Lakes, Michigan in the United States. We have big lakes there too. I just would like to advertise to you that radionuclide technology is one of the 4 technologies in the IMS, and that you should also consider the benefits of having radionuclide analysts at your NDC for a number of reasons, not only including for nuclear disasters, but that is also an important thing. And finally, one other comment is, I hope in your planning you can consider a sustainment plan. So your analysts continue to come back many, many times to these kinds of meetings, and we just don't see you once. We want to see you many, many times. So that should be in your thinking about how to sustain it for a long time. Thank you.
I didn't very well catch if there's possibility to repeat in a simpler language. And if it's possible to speak in French, it can help me.
So I'm sure you can speak in French just after the session. Is there any other question from the floor? Yeah. Thank you, Jean. Any other question for this presentation?
The next one? Yeah. Okay, the next presentation will be estimation of antineutrino registration as a method of monitoring nuclear explosion. Dr. Grichuk, please.
Good afternoon, ladies and gentlemen. My name is Roman Bisonov, and I am 4th year student of information. Oh, sorry. It's not? No. It's not our presentation. Good afternoon, ladies and gentlemen. My name is Bisonov Roman, and I am a 4th year student of Nuclear Research University, MEFI.
Hello, my name is Vadim Grichuk, and I am also a 4th year student of Information Security, MEFI. Today we will talk about a possible method of registering nuclear weapon tests at the foreign test sites and production of nuclear weapons. This method is based on the detection of ghost particles that are the product of a nuclear reaction. These particles are called antineutrino. Have you ever heard about them?
We will talk about antineutrino. During our presentation, we will talk about method itself, and we'll explain where this method found its place in the practice. In the final part of our presentation, we will focus on antineutrino detectors and provide conclusions. Let's start. Nowadays, the CTBTO has advanced state-of-the-art technologies for registering nuclear explosions, including seismic, infrasound, hydroacoustic, and radionuclide stations. However, each of these methods is limited by the environment in which detonation takes place. However, antineutrinos will help to solve this problem. It is impossible to hide these particles. Using antineutrino detection, we will enhance we will eliminate nuclear uncertainty and increase the reliability of events.
Antineutrino is a particle with a very small mass which has no electric charge. Such particles can travel through you. Yeah, right now billions of neutrinos are traveling through you. Moreover, neutrinos can travel through planets and stars with little or no interaction with them. Of course, reducing such particles is not easy. In order to fix at least a few neutrinos, scientists built various detectors and installations.
Currently, neutrino detections uses to solve many applied tasks. For example, they use to understand the origin of the universe, to study the structure of the sun, and to study the structure of the Earth. Also, they use to monitor nuclear power plants. The introduction of antineutrino detectors into the technological cycle of nuclear power plants allows real-time monitoring of fissionable materials. It also helps to detect clandestine nuclear facilities.
In general, in order to record several events from the neutrino interaction, the detector must be large. The greater the volume of the detector, the more atoms are inside it. Therefore, there is a higher probability that some of the atoms will react with the neutrino, or in the case of a beta decay reaction of atomic nucleus with the antineutrino.
Scientists from the United States, Adam Bernstein, Todd West, Vipin Gapt, in an article published in the journal Science and Global Security, presented a formula describing the number of antineutrino interactions in the reactor. The size of the detector is determined by the requirement minimum number of interactions antineutrinos with a substance. Using this formula, it is possible to calculate the approximate dimensions of the detector, which will be suitable for its use at different distances with a constant explosion power and the number of antineutrino interactions. Estimating the required scale, we know that the volume required for its use to register at least 2 antineutrinos with a probability of 96% at a distance about 1,000 kilometers with a nuclear explosion capacity of 1 kiloton is approximately 420 cubic meters. This volume, it doesn't sound reasonable. This size is comparable to the size of water pool containing 5 lines with a length of 25 meters. By the fact, most detectors for registering of these particles, for example, Homestake, Sage, Galix, Baikal GVD, Nevot, Ice Cube, Borexina are very large. Ice Cube is a very interesting design of thousands of photosensors surrounding 1 cubic kilometer in a block of ice, which is why it is called Ice Cube.
Experimental complex Nevot is located at the MEFI campus in Moscow and is the only in the world that allows to conduct fundamental and applied research with the use of cosmic rays on the surface of the Earth over the entire range of the net angles from 0 to 180 degrees in a record energy range till 10 to the power of 10 giga-electron volt. Antineutrino, the twin brother of neutrino, are emitted at the same time as electron as a result of the beta decay of nucleus of atom. During beta decay, the neutron turns into an electron and a proton. The proton remains in the nucleus and the electron is ejected at high speed. At the same time, the third particle, antineutrino, is emitted, which preserves the lepton balance of the internuclear reaction. Certainly, there are several experiments of registration of reactor antineutrinos in the world, which use different types of detectors, differing both in size and principle of operations. For example, Angra, Lucifer, Songs, iDream, and Red 100. Most of these experiments are based on the inverse beta decay reaction. There are experiments of Angra, Lucifer, Songs, Dance, and iDream.
However, recently Russian scientists from MIFI and MIPT invented the small detector, Russian emission detector Red 100, which is based on elastic scattering of neutrinos on heavy atomic nuclei. The advantage of this detector is that it is the size. The size of such detector doesn't exceed. It's comparable to the size of the refrigerator. But the advantage of this detector not only in this size, because but also in the principle of its operation. Based on this principle, the number of antineutrino interactions in this detector more in order than the number of antineutrino interactions in the detector based on inverse beta decay. Neutrino detection is guaranteed to exclude the possibility of hidden tests of nuclear weapons of any power, their development and improvement. The introduction of antineutrino detectors into the international monitoring system will facilitate the disarmament process, the construction of a peaceful and open society, and the creation of many jobs and full employment in high-technique industries.
Today, it's difficult to assess the benefits of neutrino detection. Similar to the appearance of the first computer, this is due to both the high cost, size, and restriction in the technological process. But the day is not far away when it will be as simple and obvious as the fact that the Earth is round.
Thank you for your attention. Now we are open to your questions. Please do not hesitate.
Hello, thank you for your presentation. It was really interesting. And I'd like to know, you said just a little bit about this experiment called RED. And,
Russian emission detector.
And there is a, you say that it's not an IBD effect, but something else. And there was elastic. So what is elastic stands for? I don't understand.
Thank you for your question. It is elastic because antineutrino doesn't energize a nuclei. Imagine a tennis ball and a bowling ball. The tennis ball hitting the bowling ball, and the tennis ball is like antineutrino, and bowling ball is like nuclear of atom. After interaction, the bowling ball will move just a little, but it's enough to ionization of electrons, and by this effect we will register anti-neutrino signal.
Thank you for your presentation, and my question is, why have you decided to focus on antineutrinos? Maybe it's more easier to register neutrinos.
Thank you for your question. We use antineutrinos because antineutrinos is a products of universal beta decay. When, as Vadim mentioned, when nuclear explosion takes place, there are antineutrinos. Thank you.
One more question? No, many questions.
Thank you for your presentation.
Okay.
The use of antineutrinos has been discussed for a number of years, and it's gained a lot of interest. And you're very brave to speak on this topic. I would ask that the community think about what the figure of merit is for using antineutrino detectors or for detecting any nuclear explosion. The figure of merit, I think, today has to include the dollar sign or the euro sign somewhere in the figure of merit. Because the cost of doing this, while there may be some physics that would allow it, has to include how much it will cost. There has been calculations that a 1 kiloton threshold IMS-like system built of antineutrino detectors would cost $1 trillion. There's been more than one calculation like that. So yes, you can detect it, but is anyone willing to spend $1 trillion on this? Thank you.
Thank you for your question. As I correctly understand your question, you think that antineutrino detectors are not suitable in terms of their high cost. It is true, but as I said and my colleague said, Russian scientists invented a Russian emission detector that is comparable to refrigerator. And we think that using these detectors in the future, they promises big prospects for humanity. Inverse beta decay, in which operations with big amounts of water or liquids installators, they are very large, it's true. But we think that technologies not stay, and they are developing, and maybe in the future they will reach the proper level, and the sizes and the costs of these technologies will be available.
Okay, thank you very much. Okay, next presentation is exploiting the tailorable nanoporosity of metal organic framework for in situ identification of radioisotope. Will be presented by Dr. Allendorf.
So thank you, Mr. Chairman. I'd like to tell you about a new detection concept that we're working on, which is designed to detect plumes of radioisotopes, in particular xenon, in a very short time frame. This technology is really addressing the problem that a number of the xenon isotopes of great interest have very short half-lives. As you can see here, some of them The half-life is in days or even less. And so naturally doing standoff detection requires collecting a great deal of air and extremely sensitive detectors, which the IMS has achieved, but as was alluded to in some other presentations, these are expensive and they are standoff. So we're trying to find a way where we could detect all of these. The completely automatic systems in use today are typically 12-hour collection followed by 12-hour count. And we would ask the question, is it feasible to do something that we would call real-time detection, 30 minutes or less? So some kind of time-resolved isotope concentrations. You could use this as a trigger for other systems. So we don't necessarily envision this as being a system that would be a large standoff distance, but might be small, portable, could be perhaps used in an airplane or quickly moved into place to detect a plume and then relay that information to turn on some other very sensitive equipment. Potentially, this could be used to detect very low yield threshold or very low yield explosions. So if you get anything out of this presentation, there are three things that are essential to this concept. One of them is you need a high surface area sorbent, but unlike carbon sorbents, it has to be a scintillator itself, and it has to be transparent. The second thing is we will take advantage of high pressure to increase the local concentration of the gas. So instead of letting the gas be collected at atmospheric pressure and then analyzing it, we will pressurize the gas and detect it in situ. The third thing is that instead of having a fixed volume and then collecting that over a period of time, we will have a flowing gas through this scintillating sorbent, and we will detect at short time frames intervals on the order of anywhere from 10 to 60 minutes, and the optimal time for that depends on the width of the plume. So let me introduce you to the materials that we're interested in. They're called metal organic frameworks, or MOFs for short. They've been known for about 15 years, and they're extremely high surface area materials that have been used to absorb a variety of gases, but noble gases have been studied in depth. They can perform selective uptake. Krypton and xenon selectivities have been measured. They are selective, at least a factor of 6 in some cases than nitrogen. And these are extremely stable in air, and there are now versions that can be synthesized in large quantities by commercial companies and are relatively stable to water and other atmospheric gases. Now, I don't expect you to read all of this, but the reason I put this up here is this is a table showing a number of MOFs that have been looked at for a xenon capture. And I'm listing just a few of them that are kind of representative here. Never mind the names, but they have heats of absorption that are relatively low compared to some things like silver ZSM5. So we expect that it should be relatively easy to get xenon off of this. Some have quite high selectivities, as high as 22. So these things are available, and a number of them actually could be luminescent. And luminescence is a requirement for making a scintillating material. However, most of these are not. So we have to ask the question, what properties of this MOF do we need to actually allow it to absorb xenon and then through the emission of the radioactive particles detect them via scintillation? Well, it turns out that these materials, which are crystalline supramolecular materials, we call them, that are comprised of an organic electron donor coordinated to a metal ion. So these things form as powders through a solvent and a mild heating. And so you get a material out, and many of these things have these organic type linkers that, if you're familiar with organic scintillators, they bear a very strong resemblance to them. So these are conjugated fused rings that, when ionized, can generate light through the decay of a singlet state, typically in the near UV to visible. So the point is that there are quite a few MOFs that have these kinds of moieties in them. We've actually studied these extensively, and we've been able to identify certain design parameters, design rules for getting good light output out of these. One of the big appeals of MOFs relative to many conventional absorbents is that the way that they form is pretty well understood from the conventional rules of inorganic chemistry. So you can actually envision a structure and then look at the topology of the linker and the known coordination of the metal ion and predict what kind of a structure you're going to get. So this kind of design versatility and rational design principles allows you to actually design a material for a specific purpose. So these are just an example of some of the things that would be required for a good scintillator. And for example, one of them is you want to use metal ions that have closed shells. Otherwise, you end up having quenching and absorbance of light. There's certain aspects of the topology in terms of its structure and not interacting with each other in these linkers. I won't go into the details, but suffice it to say that we have some rational concept for picking a good scintillator or designing one. Now, as I mentioned, this MOF has got to do two things. It has to absorb the xenon, but it also has to function as a scintillator, as I mentioned. So here I have plots. These are predicted xenon isotherms, so for pure xenon. And you're seeing this as a function of pressure. And the thing I want you to notice is that down here would be about one bar. And if I pressurize this gas, I can make a very dramatic increase in the concentration, the uptake by the MOF of the xenon. Now, this is pure xenon, as I mentioned, and we have nowhere near that concentration in an atmospheric sample. But what's important down here is that this is the so-called Henry's Law region, where the uptake scales with pressure. And here you can see that very slight changes in pressure can dramatically increase the uptake of this dilute material, this dilute gas. So by pressurizing the gas to, let's say, 100 bar, we can get an enormous enhancement of the concentration in our absorbent material. And here's how we've actually shown that this can be done. So here are some experiments where we've used commercial krypton. Commercial krypton has a background of krypton 85, which is a beta emitter with a very low branching ratio to give you a little bit of a gamma as well. And what we've done here is simply use detection using a MOF scintillator, and this is the absorbent called NU 1100. It has very high surface area. This is a powder, so it's not packed completely efficiently. And as I said, you were using krypton as a surrogate for xenon. So what you see here as a function of pressure is a linear plot that you would expect if you have simply an empty volume. But now if you pressurize this and you have the MOF in there, what you see is a curve that is strikingly similar to the absorption isotherm of this material. And down here, if you draw this straight line, you see here's the Henry's coefficient. So what we've done here is actually use a very expensive way of measuring an isotherm. We've done it by detecting the beta decay of krypton 85. Now, of course, we're not detecting pure krypton, as I mentioned. So we've done some simulations. It turns out that atomistic simulations using force fields for gas uptake for MOFs are extremely well developed and rather accurate. So a colleague of mine did what are called grand canonical Monte Carlo calculations and predicted gas isotherms for realistic mixtures. So he took a mixture of 100 bar of nitrogen with the atmospheric concentrations of xenon and krypton in there. This is so dilute that it took us several months to actually run the calculations. We had to run 176 million molecular dynamic steps in order for this to work. But the upshot of this is that we could predict the enhancement of the concentration in this MOF-filled volume relative to the same volume, but only at standard temperature and pressure. And depending on the MOF, we've looked at several of them here. These are all for MOFs that we think could be scintillating. You see that for xenon, you could conceivably get as much as a factor of 10 to the 4th enhancement of the concentration. So this is really a large amount right there in situ. Now, how have we done this? How have we done it practically? This is our first implementation in a laboratory test. This is a high-pressure cell, and let me describe the actual detection concept here. Here's a gas port where we would introduce pressurized gas that would flow through the system. Right here is where we would locate a small amount of a scintillating MOF sorbent. And I say small because this material has to be both transparent and not thick enough that it blocks all the light that you might want to come out of it. But it has to have, at the same point, a thickness great enough to stop the beta particles that are in there and cause scintillation to occur. So to detect that light, we use a couple of avalanche photodiodes, and then up here we have a sodium iodide detector to detect gamma particles in the conventional way. So the way, the modus operandi that we would use in an actual test would be to flow pressurized gas through here and to detect xenon, which emits both a beta particle and a gamma. We would look for coincidence of both of those particles in a certain timing band and energy range. So in that regard, it's very similar to current systems. So a very important feature of this is that we are able to distinguish against background particles, at least we've done this in the laboratory, without extensive shielding. And the reason that we can do this is that the muons are the main background that we see in our laboratory, and these can be detected coincidentally by both the sodium iodide detectors and the MOF sorbent. So anything that has this kind of a signature, we know is not coming from an adsorbed gas. So here are two examples of this, the sodium iodide PMDs, and here are the APDs. Now, in contrast, we can detect a beta event. You'll notice here that we see a signal for the APDs, but we see nothing on the sodium iodide. So that in itself is a indication that we have actually looked at a beta and not some random background event. Now, we also needed to demonstrate that we could, in fact, detect beta particles using a scintillating MOF, and that's shown here. So this is the particular MOF that we used. It has these naphthalene-type groups, which are good scintillators in general. And again, we use commercial gas in a very small cell area here, which is essentially the volume of the detection region itself. And we used a beta activity of about a becquerel per cubic centimeter, which is just the background that you have in pure krypton. So if you just look at this here, what you're seeing here are background counts here that essentially correspond to the background muon radiation. So at that point, we're simply flowing nitrogen gas through this system. And then here where you see this green peak, we turn on the valve that allows pure krypton to go through there, and immediately see a very big peak here that gives you essentially 8 sigma against the background of this system. Now this was actually at 1 bar pressure, showing that we can detect the isotope against background muons without any shielding at all. Now, a more rigorous test is what we really want to do is look at coincidence counting. I only have 2 minutes, so I'll go through this quickly. Essentially, the branching ratio for producing a gamma out of krypton-85 is really terrible. It's only 0.004. But through this analysis here, we've predicted that we should be able to see a gamma rate of about 38 per day. And you're seeing that here. These are background counts from double-scattered gammas. There are also gammas in here, but the beta gamma decay events that come from this dual coincidence counting are shown here. And this decay corresponds roughly to the 1 microsecond decay time that is known for that excited state in krypton-85. Now, the last point I want to mention to you is that in contrast to integrating for long periods of time, what we are thinking can work is that we will simply use a continuously moving average, a collection average for a very finite time window, which is shown here, an example for 10, 20, and 30 minutes and a step change. And so in each of these cases, we have different peak heights that correspond to different plume widths. And what you see is that if you match the window of this time interval approximately to the width of the plume, you will maximize that signal. And you can also see that we can get against this simulated background. So this was simply using Poisson statistics and a realistic detector geometry. One can see these peaks quite well and a continuous step change which might come from a plume that you would be flying through, for example. So I'll finish with this list of conclusions here, and then I'll let you read those and be happy to take any questions. Thank you.
Maybe we have time for one or two questions. Yes, please.
Hello, thank you. I'm Thomas. I'm from FOI in Sweden. So I wonder, how will you remove the radon that you will have in the air that you sample?
Sorry, can you say again?
The radon.
Radon?
Yeah,
Yes.
how is that removed?
Good question. Well, in principle, we think we could select out that by designing a pre-filter simply on the basis of size. Radon is larger. But truthfully, this is a problem that's already been solved for any number of monitoring stations. If nothing else, you could have a cryogenic trap that would take that out and let the rest of the gas through. That's what's done by the system that's been developed by PNNL. Works great.
Okay, thank you very much. So with this, we come to the highlight of the day, and that's the poster preview session. As indicated, I'd like to split this in two and ask the first 16 to come up, which is the poster numbers 1 till 30, including 30. So you know who you are, and let's see how good you are at self-organizing. So we want to have number 1, 3, 5, 9, 10, 12, 14, 15, 16, 17, 18, 22, 25, 27, 28, and 30. And after 30, we'll have a short amount of time to reshuffle the next 16 speakers, please. So while we wait, a reminder, there's the option to vote for best poster, best presentation through your app. Please do so.
So, good afternoon, everyone. My name is Arnaud Montpezat, and I'm very pleased to present you my work about capture and separation of xenon with a silver-doped zeolite. So basically, what we have done is we have developed a new process design to separate and purify xenon from radon, only based on adsorption with silver-doped zeolite, which is known to be one of the best material nowadays to separate xenon at room temperature and very low partial pressure. And we have also characterized its aging in process condition and the bonding between this adsorbent and the noble gases. And so if you are interested, I will be very pleased to answer your question in front of my poster P3.
Thank you.
So I'm Michael Fox. Thanks for those who came by my poster. So I was evaluating antineutrinos for nuclear exposure monitoring. Looked at both long-range IMS type applications as well as in-close for test site transparency. And both of them require very large detectors. I think it's actually 420 meters cubed, so 420 cubed meters. And so it's about 200 times the size of the Empire State Building. And so we decided that that's unfeasible for applications. But I'll be happy to answer any questions. Thanks.
Thank you.
Good afternoon. I'm Anne-Sophie Morlins from CA. I'm sure a lot of people here use MB 2005 and MB3 data to perform your analysis. So you know already the transfer function and the noise of those detectors. The past few years, our metrology lab developed means and methods to measure their sensitivity to environment parameters with enhancement in confidence. So in this poster, we present the sensitivity to static pressure and temperature. The results are very reproducible, and we encourage you to come and see the results.
Good afternoon to everyone. My name is Ivan Mikotsa. I represent Scientific and Production Enterprise Atomtex, Minsk, Belarus. Our company has developed a highly sensitive mobile radiation scanning system that can be used for locating the sites of nuclear incidents, also to search open sources and analyze surface contamination. The system function includes measurement with GPS mapping, detection, alarm, radionuclide identification, and also remote data transfer by special software. Also, the software enables to estimate gamma radiation dose rate at a height of 1 meter from the height of line. The system was successfully checked in Chernobyl relocation zone, and results are presented on our poster. Thank you very much.
So good afternoon, everyone. I'm Vincent Thomas from the French Atomic Commission. So in this portal, I will present the results I obtained during my PhD thesis. The goal was to develop a compact detector for radioxenon measurement. So it's based on a gas cell sandwiched between two sodium iodides. The gas cell is about 54 cubic centimeter, a very large volume. And in the poster, you will find the Monte Carlo simulation until the first laboratory test and xenon standard measurement. Thank you.
Hello, I'm Michael Swanwick from CREARI in Hanover, New Hampshire in the United States. We developed an electrostatic precipitator for radionuclide particle collection. That was very low power and high collection efficiency using a two-stage ESP system. We have the design flexibility to be able to change the efficiency on the fly, move our material whenever we like, and also present it to the detector in a very compact way that increases sensitivity. For this DOE grant, we first did a modeling exercise to model the performance of the system. Then we built a subscale system. And now we finally put together a full-scale prototype. In the last 2 weeks, we've had full-scale data showing 95% collection efficiency at 1,500 meters cubed per hour. Thank you.
Hi,
Hi there, I'm Chris Minto with OptiSense. We manufacture distributed fiber optic sensing systems. That is taking a fiber optic cable and splitting it up into thousands of virtual sensors. Over the last decade, we've deployed around 2 million of these around the world. They're there and being used generally for acoustic purposes. Our clients throw away the seismic data. I feel we could probably do better. So if you're interested in somewhere in the world, come and talk to me. Moreover, we can make quantitative versions of these systems for tensor strain inversion analysis. And these, as can be seen, have a noise floor below that of the global seismic noise floor. So there's a future made of glass out there with thousands of sensors. Come and speak to me if you think it could be useful. Thank you.
Okay. Hello, my name is Dobrynia from All Russia Research Institute of Automatics, and I'm here to present you our poster, an experimental setup and result of an investigation of the xenon absorption characteristic for a number of adsorbents. Basically, our poster presents an experimental setup intended to determine absorption characteristic of sorbents in different temperature. Also, you may find there a breakthroughs and all our study, results of our study. Thank you.
Good afternoon. My name is Abi Farsoni from Oregon State University in the United States. In this project, as you see here, we built and test several prototypes of beta-gamma coincident detection systems to investigate the performance of new detection mediums for atmospheric radio xenon measurements. So as you see here with our detectors, we have 3 detectors. In these detectors, we use either silicon detectors or steel band coupled to silicon photomultipliers for detecting and measuring beta and conversion electrons. And also we use CZT or new strontium iodide scintillator coupled to silicon photomultiplier for detecting X-ray and gamma rays. So please visit my poster. I would be happy to answer your questions. Thank you.
Hello, my name is Stephen Creek from Lawrence Livermore Laboratory in the United States. Particulate radionuclide stations in the IMS rely on an electromechanically or liquid nitrogen cooled detector for doing energy resolution analysis on filter papers that are collected. The problem with those systems is that anytime there's a hiccup in the power or some other issue with the station, the detectors can fail because they lose their cooling. This poster describes a system that we've engineered for NASA for some space science applications that has developed a very low power consuming detector, with the concept being it could be operated isolated from the main power of the station through a small battery and a solar cell, thereby basically eliminating that failure mode. Thanks very much.
Good afternoon. During the conference, we heard quite a few talks about novel technologies which could be beneficial for the CTBT at some point in the future. We would like to propose a neutron detector or a novel neutron detection material for on-site inspections, which is based on lithium-6 and not helium-3. On the poster, I will present our qualification measurement setup, which has been developed in the EU project ITRAP+N Phase 2, and 3 novel detection materials for neutron detection with lithium-6. And I would be happy to discuss the results with you. Thanks.
Okay, we will now start the second part of the poster presentations. So I'll ask the presenters from number 32 up to number 49 to please assemble in the correct order. And a reminder for all of you, at the end of this, please let's all meet in the posters, at the posters again to have a quick discussion. And I need to go too.
The guy left. Hi again, my name is Steve Creek, still from Livermore Lab. You've heard several poster presentation previews talking about metal organic frameworks, which are very selective to the absorption of xenon from whole air. One of the chief challenges of those materials, while some can be self-scintillating or otherwise, is the ability to produce them at scales that make it usable for applications such as the IMS. This project actually is something exploring that, looking to produce quantities that are on the scale of hundreds of grams of this material in a means that would be usable for an application like a station. Thanks very much.
So my name is Thomas Fritjof. I'm from FOI in Sweden. So the poster that we have presents the first 6-month long-term test that we did on our Sauna 3 prototype at FOI. So the poster presents a little bit about the system and then the results during this period where we actually received a system performance index of over 98% without any major outages. Thank you.
Good afternoon. Anders Ringbom, also FOI. This is a poster describing the development we have done at FOI and together also with Sensor Systems on the first industrial prototype for a noble gas system adapted for an array network. So maybe most of you have seen it. Is also in IRL here outside in the exhibition hall. It has been tested. The system has the performance of a Sauna 2 system, more or less, to a fraction of the cost. It's much smaller, easier to install, operate, and maintain. And we will, this year and the next, install a 5-system array in Sweden and to test this as a proof of concept array, the first one in the world. Thank you.
So good afternoon, everybody. So our poster, Frank Lassonnier from CA. Our poster highlights a very challenging and specific topic, which is dedicated to improvement and confidence in measurement in the low frequency dynamic quantities, especially for infrasound and seismic sensors. CA, as you know maybe, is working on that field for many, many years, and our poster present the current activities in that field. We can split these activities in 5 parts. The first one is the development of standards. The second one is the development of calibration methods. The third one is comparison with other international institutes in order to get validation of methods. After, we develop calibration system and software, and we improve calibration and testing environment to do all these measurements. And at the end, we have quality organization to control all these activities. Thank you very much.
Good afternoon. I am Mariana Ditada from INVAP in Argentina, and our poster presents the status of the stack monitor for the stacks project. The stack is the source term analysis of xenon. So we have made a design that is based on a germanium detector, and it is adaptable to a broad radioxenon emission regimes of the different radioisotope production facilities. It has a modular design, and if you come to the poster, you will see what's the status. It's already designed, and all the parts are being manufactured. We already have the detector, and it is going to be tested in a radioisotope production facility that is working in Argentina, and it has to be finished by February 2020. Thank you.
Good afternoon, I'm Christophe Gueb from the Belgian Nuclear Research Center. In this poster, we present a project which started at the end of last year on studying xenon adsorption materials for IMS noble gas stations. So it's a EU Joint Action 7 program-funded project in support of the CTBT. So as you have seen, there are metallic organic frameworks, a new type of adsorbent materials, which have been recently studied for xenon adsorption, but it was very specific conditions, in fact, for xenon-krypton separation, so at very different conditions than for IMS conditions. So in this project, we are looking to these materials, but really for conditions which are IMS, noble gas station relevant. So I'm at poster 38, so if you want to discuss this and see the project, come and see. Okay, thank you.
Hi, my name is Eddie Tillestrand. I'm with General Dynamics. We operate the US IMS radionuclide stations for the network. So we did a limited test of a commercially available cosmic veto system on the RASA particulate sampler with no additional hardware modifications, and we quantified the effect of the MDC. So if you want to learn more, come see me at the poster. Thanks.
Good evening, everyone. My name is Lindsay. I'm from the Swedish Defense Research Agency. We have developed a new concept for radio xenon detection called Sana Cube. In this poster, we will give you a detailed information regarding the gas processing system. We have run the system continuously for more than 4 months, which showed excellent yield and separation results. Thank you.
Good afternoon, everyone. My name is Libby Patty from Graup Systems Limited. We've been a supplier to the seismic array of the International Monitoring System for many years, including our DM24 digitizer. We're now happy to have available our new Affinity digitizer, specifically designed for the IMS. The primary design focus was to minimize the changes in operation to the digitizer, to minimize the learning curve for station operators. Today we present test results from Sandia National Labs. Thank you very much.
Hello, I'm Klaus Hermannspan from the PTS CTBTO, and we're responsible for operating the IMS and keeping everything going. When it comes to the radionuclide part of the IMS, there's a lot of talk about detection systems, but there's also some sampling that needs to be done, and so we use these type of filter materials. And the question that the topic that I discuss in my poster is how to test and validate these type of filter materials that they comply with our requirements and they're fit for use. Thank you very much.
Good afternoon. I'm Yoshi Kaneda from Kagawa University. In Japan, we have many real-time monitoring systems such as HiNet, DoNet, and SNet. Especially the DoNet at the next megathrust earthquake in the Nankai Trough. DoNet will provide the more important information, especially the early warning of the earthquake and the tsunamis, and provides the real-time inundation simulation. And finally, we provide the transfer prediction information. This information is very, very important for the evacuation and the preparedness. So I will introduce this DoNet function at the poster. Thank you very much.
Hello, I'm Alan Seifert from Pacific Northwest National Laboratory. This poster presents the potential for doing ultrasensitive measurements of large volume radio xenon samples using an ultra-low background proportional counter. The motivation for this work is the characterization of regional xenon backgrounds around the globe. As you may have seen on several talks throughout the week, PNNL has developed an ultra-low background proportional counter technology that's used for a number of different applications, including argon-37 and argon-39 measurements. In this work, we tested a variety of different xenon gas blends at different operating pressures, and ultimately arrived at a 98% xenon, 2% methane gas blend operating at 3 atmospheres. This sample in the detector represents the equivalent of roughly 3,000 cubic meters of whole air and has a measurement sensitivity that is more than an order of magnitude lower than atmospheric backgrounds. Thanks.
Good afternoon. My name is Laurel Sinclair. I'm with Natural Resources Canada. The sensor that we've developed is a very high sensitivity gamma sensor that's also able to point out the direction to a radioactive source in motion. We've put this sensor on a UAV. I've got some very exciting live source trial data shown on my poster for you to see. You can see how the sensor is pointing to a source as it's traveling past it. You can also see if the sensor is restricted outside of the perimeter of a zone in an on-site inspection. It can still kind of triangulate to give you the distribution of a source that's inside that zone.
Okay, last one for the day. Excuse my voice. My name's Jim Hayes from Pacific Northwest National Laboratory, and I'm presenting a poster on Xenon International, kind of a revolutionary new design in radio xenon detection systems. We focused on improving detection sensitivity. We've reached about a factor of 2 better than the IMS systems right now on a 6-hour time scale, and we've focused heavily on the reliability of the system. We've also finished a 1-year field test where the Xenon International was next to the USX75 system for 1 year, and we've got the test results for that. And if you want to see a full-size mock-up, see the Teledyne Brown Engineering booth. They have a full-size system. The system's been transitioned fully to a manufacturer, Teledyne Brown Engineering. So come see my poster, talk to me, see the display. Thank you.
Thank you very much. Couple of things to say. First of all, a reminder to all of you, this session on sensor systems and advanced technologies will continue tomorrow morning, 8 a.m., this very room. No, sorry, 9 a.m., this very room. You can come early if you like. Secondly, let's thank all of the speakers of today's session. And yeah, maybe let's meet at the posters for a quick discussion.
Some highlights to your document. Or do you want I send it to you? Do you want I send it to you by email? I write them now? Yeah. Can I send it to you by email? Yeah. Now. Do you want to discuss with Ricardo some highlights? If this fine is the one you propose?
Yeah.
Ricardo, have you looked at the highlights that Klaus prepared, or did you check your email maybe today? No. No. Okay. So because by the end of today.